x with respect to position. And substituting an xt here doesn't really do anything. There's no derivatives here, so this is not a particularly interesting term. So we're getting v xt. All right. Now the next step in separation of variables is to divide through by your solution, xt, assuming it's not 0, that's okay. And you end up with I h bar 1 over big T, canceling out the x, and you're just left with big T. 1 over t, partial of t dt. And then on the right-hand side, we have minus h bar squared over 2m, 1 over big X, second partial of x with respect to position, plus v. X and t are fully canceled out in this term. Now, as before, this is a function of time only, and this is a function of space only, which means both of these functions have to be constant. And in this case, the constant we're going to use is E. And you'll see why once we get into talking about the energy in the context of the wave function. So we have our two equations. One, I h bar over t, first partial derivative of big T with respect to time, is equal to E. And on the right-hand side, from the right-hand side, we get minus h bar squared over 2m, 1 over big X, second partial of big X with respect to position, plus V is equal to the energy. So these are our two equations. Now I've written these with partial derivatives, but since, as I said before, these functions, big T and big X, are only functions of a single variable, there's effectively no reason to use partial derivative symbols. I could use d's instead of partials. Essentially, there's no difference if you only have a function of a single variable, whether you take the partial derivative or the total derivative. So, let's take these equations one by one. The first one, the time part. This we can simplify by multiplying through by big T, as before, and you end up with I h bar d big T dt equals E times T. Taking the derivative of something and getting it back, multiplied by a constant, again should suggest two exponentials. Let me move this I h bar to the other side. So we would have divided by I h bar, and 1 divided by I is minus I. So I'm going to erase this from here and say minus I in the numerator. So first derivative with respect to time of our function gives us our function back with this out front. Immediately this suggests exponentials, and indeed our general solution to this equation is some normalization constant times e to the minus I e over h bar times time. So if we know what this separation constant, capital E, is, we know the time part of the evolution of our wave function. This is good. What this tells us is that our time evolution is actually quite simple. It's in principle a complex number. T is, in principle, a complex number. It has constant magnitude. Time evolving this doesn't change the absolute value of capital T. And essentially it's just rotating about the origin in the complex plane. So if this is my complex plane, real axis, imaginary axis, wherever capital T starts, as time evolves, it just rotates around and around and around and around in the complex plane. So the time evolution that we'll be working with, for the most part, in quantum mechanics is quite simple. The space part of this equation is a little more complicated. All I'm going to be able to do now is rearrange it a little bit by multiplying through by capital X, just to get things on top, and change the order of terms a little bit to make it a little more recognizable. Minus h bar squared over 2m, second derivative of capital X with respect to position plus v times capital X is equal to E times capital X. And this is all the better we can do. We can't solve this equation because we don't know what v is yet. V is where the physics enters this equation and where the wave function from one scenario differs from the wave function for another scenario. Essentially, the potential is where you encode the environment into the Schrodinger equation. Now, if you remember back a ways, when we were talking about the Schrodinger equation on the very first slide of this lecture, what we had was the Hamiltonian operator acting on the wave function. And this is that same Hamiltonian. This is h hat, not acting on psi now, just acting on x. So you can also express the Schrodinger equation as h times x equals E times x. The Hamiltonian operator acting on your spatial part is the energy of, is the separation constant E, which is related to the energy, times the spatial part. So this is another expression of the Schrodinger equation. This equation itself is called the time-independent Schrodinger equation, or TISE if I ever use that abbreviation. And this is really the hard part of any quantum mechanics problem. To summarize what we've said so far, starting with the Schrodinger equation, which is this, time derivatives with complex parts in terms of Hamiltonians and wave functions gives you this, substituting in the actual definition of the Hamiltonian, including a potential v, and applying separation of variables gets us this pair of ordinary differential equations. The time part here gave us numbers that just basically spun around in the complex plane. Not the imaginary part. This is traditionally the real part, and this is the imaginary part. So the time evolution is basically rotation in the complex plane. And the spatial part, well, we have to solve this equation being the time-independent Schrodinger equation. We have to solve this for a given potential. The last comment I want to make in this lecture is a comment about notation. My notation is admittedly sloppy, and if you read through the chapter, Griffiths calls my notation sloppy. In Griffiths, since it has the luxury of being a book and not the handicap of having my messy handwriting, they use capital psi to denote the function of x and time. And when they do separation of variables, they re-express this as lowercase psi as a function of position and lowercase phi as a function of time. So for this, I used capital X. Sorry, I should put things in the same order. I used capital T of t and capital X of x, because I have a better time distinguishing my capital letters from my lowercase letters than trying to, well, you saw how long it took me to write that symbol. I'm not very good at writing capital psi. There is a lot of sloppiness in the notation in quantum mechanics, namely because, oops, geez, I have two functions of time. This is Griffith's function of position. Sorry about that. This here and this here, these are really the interesting parts, the functions of position, the solutions to the time-independent Schrodinger equation. What that gives us, well, what that means is that a lot of people are sloppy with what they call the wave function. This is the wave function. This is the spatial part, or the solution to the time-independent Schrodinger equation. This is not the wave function. But, I mean, I've already made this sloppy mistake a couple of times in problems that I've given to you guys in class. Namely, I'll ignore the time domain part and just focus on the spatial part, since that's the only interesting part. So, perhaps that's my mistake. Perhaps I need to relearn my handwriting. But, at any rate, be aware that sometimes I, or perhaps even Griffiths, or whoever you are talking to, will use the term the wave function when they don't actually intend to include the time dependence. And the time dependence is, in some sense, easy to add on because it's just this rotation in complex number space. But hopefully things will be clear from the context what is actually meant by the wave function. So we're still moving toward solutions to the Schrodinger equation. And the topic of this lecture is what you get from separation of variables and the sorts of properties it has. To recap what we talked about last time, the Schrodinger equation, I h bar partial derivative of psi with respect to time is equal to minus h bar squared over 2m second partial derivative of psi with respect to position plus v times psi, where this is essentially the kinetic energy and this is the potential energy as part of the Hamiltonian operator. We were able to make some progress towards solving this equation by writing psi, which is in principle a function of position and time, as some function of position multiplied by some function of time. Why did we do this? Well, it makes things easier. We can make some sort of progress, but haven't we restricted our solution a lot by writing it this way? Well, really we have, but it does make things easier, and it turns out that these solutions that are written as products that result from solving the ordinary differential equations you get from separation of variables with the Schrodinger equation can actually be used to construct everything that you could possibly want to know. So let's take a look at the properties of these separated solutions. First of all, these solutions are called stationary states. What we've got is psi as a function of position and time is equal to some function of position multiplied by some function of time. And I wrote that as capital T on the last slide, but if you remember from the previous lecture, the time evolution equation was solvable, and what it gave us was a simple exponential, e to the, minus I times e times t divided by h bar. So this is our time evolution part, and this is our spatial part. What does it mean for these states to be stationary? Well, consider, for instance, the probability density for the outcome of position measurements. Hopefully you remember this is equal to the squared absolute magnitude of psi, which is equal to the complex conjugate of psi times psi. Now if I plug this in for psi and its complex conjugate, I end up with the complex conjugate of big X as a function of position times the complex conjugate of this. The only part that's complex about this is the I here in the exponent, so we need to flip the sign on that. And we'll have e to the I, positive I now, e t over h bar. That's for the complex conjugate of psi. And for the psi itself, well, x of x e to the minus I e t over h bar. Now, multiplying these things together, there's nothing special about the multiplication here, and this are complex conjugates of each other, so they multiply together to give the magnitude of, the squared magnitude of each of these numbers together, which, since these are just complex exponentials, is magnitude 1. So what we end up with here is x star x, essentially the squared magnitude of just the spatial part of the wave function. There's now no time dependence here, which means the probability density here does not change as time evolves. So that's one interpretation of one meaning of these things being called stationary states. The fact that I can write a wave function as a product like this, and the only time dependence here comes in a simple complex exponential, means that that time dependence drops out when I find the probability distribution. Another interpretation of these things as stationary states comes from considering expectation values. Suppose I want to calculate the expectation value of some generic operator, capital Q. The expression for the expectation of an operator is an integral of the wave function times the operator acting on the wave function. So complex conjugate wave function, operator, wave function. Now I'm going to go straight to the wave function as expressed in terms of x and t parts. So complex conjugate of the spatial part times the complex conjugate of the time part, which from the last slide is e to the plus I e t over h bar. Our operator gets sandwiched in between the complex conjugate of the wave function and the wave function itself. So this is again, no stars anymore, come on Brett, just x and then e to the minus I e t over h bar. And this is all integrated dx. So this is psi star, and this is psi. And this is our operator sandwiched between them, as in the expression for the expectation. Now, provided this operator does not act on time, it doesn't have anything to do with the time coordinate, and that will be true for basically all of the operators we will encounter in this course. Now, we talked about how the Schrodinger equation can be split by separation of variables into a time-independent Schrodinger equation and a relatively simple time-dependent part. What that gave us is, provided we have solutions to that time-independent Schrodinger equation, we have something called a stationary state. And it's called a stationary state because nothing ever changes. The probability densities are constant, the expectation values are constant, and the state effectively, since it has a precise, exact, no uncertainty energy, has to live for an infinite amount of time. That doesn't sound particularly useful. From the perspective of physics, we're often interested in how things interact and how things change with time. So how do we get things that actually change with time in a non-trivial way? Well, it turns out that these stationary states, while their time dependence is trivial, the interaction of their time dependence when added together in a superposition is not trivial. And that's where the interesting time dynamics of quantum mechanics comes from. Superpositions of stationary states. Now we can make superpositions of stationary states because of one fundamental fact, and that fact is the linearity of the Schrodinger equation. So the Schrodinger equation, as you hopefully remember it by now, is I h bar partial derivative of psi with respect to time is equal to minus h bar squared over 2m second derivative of psi with respect to x, and that's a really ugly psi. Must fix. Second derivative of psi with respect to position plus v times psi. So this is our Hamiltonian operator applied to the wave function, and this is our time dependence part. Now, in order for an equation to be linear, what that means is that if psi solves the equation, psi plus some other psi that also solves the equation will solve the equation. So if, say, let's call it A, solves the Schrodinger equation, and B solves the Schrodinger equation, and let me write this out in a little more detail. First of all, I'm talking about A is a function of position and time, as is B. If A and B both solve the Schrodinger equation, then A plus B must also solve the Schrodinger equation. And we can see that pretty easily. Let's substitute psi equals A plus B into this equation. The first step, I h bar partial derivative with respect to time of A plus B is equal to minus h bar squared over 2m second partial derivative with respect to space of A plus B plus the potential V times A plus B. Now the partial derivative of the sum is the sum of the partial derivatives. That goes for the second partial derivative as well. And well, this is just the product of the potential with the sum is the sum of the product of the potential with whatever you're multiplying out. I'm going to squeeze things a little bit more here. So I can write that out. I h bar d by dt of A plus I h bar dB dt equals minus h bar squared over 2m second derivative of A with respect to space. Oh, forgot my squared on the second derivative. Minus h bar squared over 2m second derivative of B with respect to position plus V times A plus V times B. That's just following those fundamental rules. Now, you can probably see where this is going. This, and this. These three terms together make up the Schrodinger equation, the time-dependent Schrodinger equation for A. For A. For A. And this, and this altogether, that's the time-dependent Schrodinger equation for B. So if A satisfies the time-dependent Schrodinger equation, which is what we supposed when we got started here, then this term, and this term will cancel out. They will obey the equality. Likewise, for the parts with B in them. So essentially, if A solves the Schrodinger equation and B solves the Schrodinger equation, A plus B also solves the Schrodinger equation. And the reason for that is the partial derivatives here. The partial derivative of the sum is the sum of the partials, and the product with the sum is the sum with the product. These are linear operations, so we have a linear partial differential equation, and the linearity of the partial differential equation means, well, essentially that if A solves and B solves, then A plus B will also solve it. That allows us to construct solutions that are surprisingly complicated. And actually, the general solution to the Schrodinger equation is psi of position and time is equal to the sum, and I'm going to be vague about the sum here. You're summing over some index j, x sub j, as a function of position. These are solutions now to the time-independent Schrodinger equation, the spatial part of the Schrodinger equation, times your time part. And we know the time part from the, well, back from when we discussed separation of variables, is minus I e, now this is going to be e sub j, t, over h bar. So this is a general expression that says we're summing up a whole bunch of stationary state solutions to the time-independent Schrodinger equation. And we're getting psi. Now, I've left something out, and what I've left out is quite important here. We need some constant, c sub j, that tells us how much of each of these stationary states to add in. So this is actually, well, it's going to be a solution to the Schrodinger equation since it's constructed from solutions to the Schrodinger equation. And this is completely general. That's a little surprising. What that means is that this can be used to express not just a subset of solutions to the Schrodinger equation, but all possible solutions to the Schrodinger equation. All the solutions to the Schrodinger equation can be written like this. That's a remarkable fact, and it's certainly not guaranteed. You can't just write down any old partial differential equation, apply separation of variables, and expect the solutions that you get to be completely general and superposable to make any solution you could possibly want. The reason this works for the Schrodinger equation is because the Schrodinger equation is, well, just to drop some mathematical terms if you're interested in looking up information later on, the Schrodinger equation is an instance of what's called a Sturm-Liouville problem. Sturm-Liouville problems are a class of linear operator equations, for instance, partial differential equations or ordinary differential equations, that have a lot of really nice properties. And this is one of them. So the fact that the Schrodinger equation is a Sturm-Liouville equation, or the fact that the time-independent Schrodinger equation is a Sturm-Liouville equation, means that this will work. So if you go on to study, advanced mathematical analysis methods in physics, you'll learn about this. But for now, you just need to sort of take it on faith that general solutions to the Schrodinger equation look like this. Superpositions of stationary states. So if we can superpose stationary states, what does that actually get us? One example I would like to do here is, and this is just an example of the sorts of analysis you can do given superpositions of stationary states, is to consider the energy. Suppose I have two solutions to the time-independent Schrodinger equation, which I'm just going to write as h hat x1 equals E1 x1, and h hat x2 equals e2 x2. So x1 and x2 are solutions to the time-independent Schrodinger equation, and they're distinct solutions. E1 not equal to E2. I'm going to use these to construct a wave function, let's say psi, of x, and at time t equals 0, let's say it looks like this. C1 times x1 as a function of position plus. Quantum mechanics is really all about solving the Schrodinger equation. That's a bit of an oversimplification, though, because if there was only one Schrodinger equation, we could just solve it and be done with it, and that would be it for quantum mechanics. The reason this is difficult is that the Schrodinger equation isn't just the Schrodinger equation. There are many Schrodinger equations. Each physical scenario for which you want to apply quantum mechanics has its own Schrodinger equation. They're all slightly different, and they all require slightly different solution techniques. And the reason there are many different Schrodinger equations is that the situation under which you want to solve the Schrodinger equation enters the Schrodinger equation as a potential function. So let's talk about potential functions and how they influence, well, the physics of quantum mechanics. First of all, where does potential appear in the Schrodinger equation? This is the time-dependent Schrodinger equation, and the right-hand side here, you know, is giving the Hamiltonian operator acting on the wave function. Now, the Hamiltonian is related to the total energy of the system, and you can see that by looking at the parts. This is the kinetic energy, which you can think of as the momentum operator squared over 2m, sort of a quantum mechanical analog of p squared over 2m in classical mechanics. And the second piece here is, in some sense, the potential energy. This V of x is the potential energy as a function of position. As if this were a purely classical system. For instance, if the particle is found at a particular position, what would be its potential energy? That's what this function V of x encodes. Now, we know in quantum mechanics we don't have classical particles that can be found at particular positions. Everything is probabilistic and uncertain, but you can see how this is related. This is the time-dependent Schrodinger equation, which is a little bit unnecessarily complicated. Most of the time, we work with the time-independent Schrodinger equation, which looks very similar. Again, we have a left-hand side given by the Hamiltonian. We have a kinetic energy here, and we have a potential energy here. If we're going to solve this time-independent equation, note now that the wave functions here are expressed only as functions of position, not as functions of time. This operator gives you the wave function itself back multiplied by e, which is just a number. This came from the separation of variables. It's just a constant. And we know from considering the expectation value of the Hamiltonian operator, which is related to the energy, for solutions to this time-independent Schrodinger equation, that we know this is essentially the energy of the state. Now, what does it mean here in this context, or in this potential context? Well, you have a potential function of position, and you have psi, the wave function. So this v of x psi of x, if that varies as a function of position, and it will, if the wave function has a large value, a large magnitude in a certain region, and the potential has a large value in a certain region, that means that there is some significant probability the particle will be found in a region with high potential energy. That will tend to make the potential energy of the state higher. Now, if psi is 0 in some region where the potential energy is high, that means the particle will never be found in a region where the potential energy is high. That means the state likely has a lower potential energy. This is all a very sort of heuristic qualitative argument, and we can only really do better once we know what these solutions are and what these actual potential functions look like. What I'd like to do here before we move on is to rearrange this a little bit to show you what effect the potential energy related to the energy and how it's related to the energy of the state, what effect that has on the wave function. And in order to do that, I'm going to multiply through by this h bar squared over 2m, and rearrange terms a little bit. What you get when you do that is the second derivative of psi with respect to x. There's my eraser. With respect to x being equal to 2m over h bar squared times v of x minus e psi. So this quantity here relates the second derivative of psi to psi itself. For instance, if the potential is larger than the energy of the state, you'll get one overall sign relating the second derivative in psi, whereas if energy is larger than potential, then you'll end up with a negative quantity here relating the second derivative of psi with itself. So keep this in the back of your mind, and let's talk about some example potential functions. This is what we're going to be doing, or this is what the textbook does in all of Chapter 2. Write different potential functions and solve the Schrodinger equation. The first example potential we do, and this is section 2.2, is what I like to call the particle in a box. The textbook calls it an infinite square well. The particle in a hard box, for instance, you can think of as a potential function that looks like this. Get myself some coordinate systems here. You have a potential function v of x, oops, turn off my ruler, that looks something like this. This is v of x as a function of x. The potential goes to infinity for x larger than some size. Let's call this, minus a to a. If you're inside minus a to a, you have zero potential energy. If you're outside of a, you have infinite potential energy. It's a very simple potential function. It's a little bit non-physical, though, because, well, infinite potential energy, what does that really mean? It means it would require infinite energy to force the particle beyond a. If you had some infinitely dense material that just would not tolerate the electron ever being found inside that material, and you made a box out of that material, this is the sort of potential function you would get. Much more realistically, we have the harmonic oscillator potential. The harmonic oscillator potential is the same as what you would get in classical physics. It's a parabola. This is something, proportional to x squared. V of x being proportional to x squared is what I mean. This is what you would get if you had a particle attached to a spring connected to the origin. If you move the particle to the right, you stretch the spring. Put quantum mechanically, if you happen to find the particle at a large displacement from the origin, the spring would be stretched quite a large amount and would have a large amount of potential energy associated with it. From a more physical, down-to-earth sort of perspective, this is what happens when you have any sort of equilibrium position for a particle to be in. The particle is sitting here near the origin where there is a flat potential, but any displacement from the origin makes the potential tend to increase in either direction. This is like an electron in a particle trap, or an atom in a particle trap. Harmonic oscillator potentials show up all over the place, and we'll spend a good amount of time talking about them. The next potential that we consider is the delta function potential. And what that looks like, now I'm going to start at 0 and draw it going negative, but it's effectively an infinitely sharp, infinitely deep version of this particle in a box potential. Instead of going to infinity outside of your realm, it's at 0, and instead of being at 0 inside your realm, it goes to minus infinity there. This now continues downwards. It doesn't bottom out here. The overall behavior will be different now because the particle is no longer disallowed from being outside of the domain. There is no longer an infinite potential energy here. And we'll talk about that as well. These are all sort of weird, non-physical potentials. The particle in a soft box potential is a little bit more physical. If I have my coordinate system here, the particle in a soft box potential looks something like this. To keep things simple, it still changes instantaneously at, say, minus a and a, but the potential energy is no longer infinity. This is, for instance, a box made out of a material that has some pores in it, and the electron, or whatever particle you're considering to be in the box, doesn't like being in those pores. So there's some energy you have to add in order to push the particle in. Once it's in, it doesn't really matter where it is. you've sort of made that energy investment to push the particle into the box. And we'll talk about the quantum mechanical states that are allowed by this potential as well. Finally, we will consider what happens when there's no potential at all. Essentially, your potential function is constant. That actually has some interesting implications for the form of the solutions of the Schrodinger equation. And we'll talk about that in more detail. To map this onto textbook sections, this is section 2.2. The harmonic oscillator is section 2.3. The delta function potential is section 2.5. The particle in a box is section 2.6. Particle in a soft box is 2.6. And particle with no potential or an overall constant potential everywhere in space is section 2.4. So these are some example potentials that we'll be talking about in this chapter. What do these potentials actually mean, though? How do they influence the Schrodinger equation and its solutions? Well, the way I wrote the Schrodinger equation a few slides ago, second derivative of psi with respect to x is equal to 2m over h bar squared, just a constant, times v of x minus e psi. This is now the time-independent Schrodinger equation, so we're just talking about functions of position here. And E, keep in mind, is the energy of the state. If we're going to have a solution to the time-independent Schrodinger equation, this E exists, and it's just a number. So what does that actually mean? Let's think about it this way. We have a left-hand side determined by the right-hand side of this equation. And the left-hand side is just the second derivative with respect to position of the wave function. This is related to the curvature of the wave function. I could actually write this as a total derivative, since this is just psi is only a function of position now. So there's no magic going on with this partial derivative. It's going to behave same as the ordinary derivative that you're used to from calculus class. The second derivative is related to the concavity of a function, whether something's concave up or concave down. So let's think about what this means. If you have a potential v of x that's greater than your energy, if v of x is greater than E, what does that mean? That means v of x minus E is a positive quantity. That means the right-hand side here will have whatever sign psi has. And I'm being a little sloppy since psi here is in general a complex function. But if we consider it to just be, say, positive, which isn't as meaningful for a complex number as it is for a real number, you would have psi of x. If psi of x is positive and this number is positive, then the second derivative is positive. Which means that if psi is, say, here, psi is positive, when it's multiplied by is positive, then the second derivative is positive. It curves like this. Whereas if psi is down here, psi is negative, this is positive, second derivative of psi is negative. It curves like this. What this means is that psi curves away from our axis, away from this psi equals 0 line. On the other hand, if v of x is less than the energy, this quantity will be negative, and we get the opposite behavior. If psi is up here, positive, it's multiplied by a negative number, and the second derivative is negative, you get something that curves downwards. If psi is on the other side of the axis, it curves upwards. Psi curves toward the axis. So this helps us understand a little bit about the shape of the wave function. For instance, let me do an example here in a little bit more detail. Suppose I have, I'll do it over here, coordinate system. If I have a potential function, let's do the sort of soft particle in a box. I can do better than that. Soft particle in a box. So v of x is constant outside your central region and constant inside your central region and has a step change at the boundaries of your region. Let's think about what our wave function might look like. under these circumstances. So we have our boundaries of our region here. The other thing that we need to know to figure out what the wave function might look like is a hypothetical energy. And I'm just going to set an energy here. I'm going to do the interesting case. Let's say this is the energy. And I'm plotting energy on the same axis as the potential, which is fine. This is the energy of the state. This is the potential energy as a function of position, so they have the same units. What this energy hypothetically means is that outside here, the potential energy is greater than the energy of the state, and inside here, the potential energy is less than the energy of the state. So we'll get different signed sort of behaviors, different curvatures of the wave function. So, do my wave function in blue here. If I say, start my wave function, this is all hypothetical now, this may not work. If I start my wave function here, at some point on the positive side of the axis, at the origin, we know the energy of the state is larger than the energy of, or than the potential energy. So this quantity is negative, and psi curves towards the axis. So since psi is positive here, I'm looking at this sort of curvature. So I could draw my wave function out sort of like this. Maybe that's reasonable, maybe that's not. This is obviously not a quantitative calculation. This is just sort of the sort of curvature that you would expect. Now, I only continue these curving lines out to the boundaries, since at the boundaries, things change. Outside our central region here, the potential energy is larger than the energy of the state, and you get curvature away from the axis. What might that look like? Well, something curving away from the axis. It's going to look sort of like that. But where do I start it? Do I start it going like that? Do I start it going like that? What does this actually look like? Well, if you think about this, we can say a little bit more about what happens to our wave function when it passes a boundary like this. And the key fact is that if v of x is finite, then while we might have the second derivative of psi with respect to x being discontinuous, maybe, might not be. In this case, the second derivative of psi is just set by this difference. So when we have a discontinuity in the potential, we have a discontinuity in the second derivative. The first derivative of psi will be continuous. Think about integrating a function that looks like this. I integrate it once, I get something maybe with large positive slope going to slightly smaller positive slope. There will be no discontinuity in the first derivative. What this means for psi is that it's effectively smooth. And that by that I just sort of mean no corners. The first derivative of psi won't ever show a corner like this. It will be something like that, for example. No sharp corners to it. What that means in the context of a boundary like this is that if I have psi going downwards at some angle here, I have to keep that angle as I cross the boundary. Now once I'm on the other side of the boundary here, I have to curve. And I have to curve according to the rules that we had here. So depending on what I actually chose for my initial point here and what the actual value of the energy was and what the actual value of the potential is outside in this region, I may get differing degrees of curvature. I may get something that happens like this, curves up very rapidly, or I may get something that doesn't curve very rapidly at all. Perhaps it's curving upwards very slowly, but it crosses the axis. Now, as it crosses the axis, the sign on psi here changes. The curvature is also determined by psi. As psi gets smaller and smaller, the curvature gets smaller and smaller, the curvature becoming zero as psi crosses the axis. Then when psi becomes negative, the sign of the curvature changes, so this would start curving the other direction, curving downwards. It turns out that there is actually a state right in the middle, sort of a happy medium state, where psi curves, and just kisses the axis. Comes towards the axis, and when it comes towards the axis and reaches the axis with zero slope and zero curvature, it's stuck. It will never leave the axis again. And these are the sorts of states that you might actually associate with probability distributions. You know, if psi is blowing up like this, going to positive infinity or to negative infinity, that your wave function will not be normalizable. But the wave function here, denoted by these green curves, has finite area, therefore is sort of normalizable. So these are the sorts of things that the potential function tells you about the wave function. In general, what direction it curves, how much it curves, and how quickly. And of course, doing this quantitatively requires a good deal of mathematics. But I wanted to introduce the math, or before I introduce the math, I wanted to give you some conceptual framework with which to understand what exactly this potential means. If the potential is larger than the energy, you expect things that curve upwards. And when you get things that curve upwards, you'll have, or curve away from the axis, you tend to have things blow up unless they just sort of go down and kiss the axis like this. So there will be a lot of things approaching the axis and never leaving, so that we have normalizable wave functions. On the other hand, if the potential energy is less than the energy of the state, you get things that curve towards. And well, if you have something that curves towards, it tends to do this. Always curving towards, always curving towards, always curving towards the axis. You get these sort of wave-like states. So that's a very hand-waving discussion of the sorts of behavior you get from, in this case, step discontinuous potential. And we'll see the sort of behavior throughout this chapter. To check your understanding, take this step discontinuous potential and tell me which of these hypothetical wave functions is consistent with the Schrodinger equation. Now, I did not actually go through and solve the Schrodinger equation here to make sure these things are quantitatively accurate. They're probably all not quantitatively accurate. What I'm asking you to do here is identify the sort of qualitative behavior of these systems. Is the curvature right? And let's see. Yeah, are the boundary conditions right? In particular, does the wave function behave as you would expect as it passes from the sort of interior region to the exterior region? We've been talking about solving the Schrodinger equation and how the potential function encodes the scenario under which we're solving the Schrodinger equation. The first real example of a solution to the Schrodinger equation and a realistic wave function that we will get comes from this example, the infinite square well, which I like to think of as a particle in a box. The infinite square well is called that because its potential is infinite and, well, square. What the potential ends up looking like is, if I plot this, going from 0 to A, the potential is infinity if you're outside the region between 0 and A, and at 0 if you're in between the region, if you're in between 0 and A. So what does this look like when it comes to the Schrodinger equation? Well, what we'll be working with now is the time-independent Schrodinger equation, the TISE, which reads minus h bar squared over 2m times the second derivative of, sorry, I'm getting ahead of myself, the second derivative of psi with respect to x plus potential as a function of x times psi is equal to the energy of the stationary state that results from the solution of this equation times psi. Now, this equation doesn't quite look right if we're outside the region. Bad things happen. You end up with an infinity here for v of x, if x is not between 0 and a. The only way this equation can still make sense under those circumstances is if psi of x is equal to 0, if x is less than 0 or x is greater than a. So outside this region, we already know what our wave function is going to be. It's going to be 0, and that's just a requirement on the basis of infinite potential energy. Can't really exist in the real world. Now, what if we're inside? Then v of x is 0, and we can cancel this entire term out of our equation. What we're left with then is minus h bar squared over 2m, second partial derivative of psi, with respect to x, is equal to e times psi, just dropping that term entirely. So this is the time-independent Schrodinger equation that we want to solve. So how do we solve it? Well, we had minus h bar squared over 2m times the second derivative of psi with respect to x being equal to e times psi. We can simplify that just by rearranging some constants. What we get, minus second derivative of psi with respect to x equal to minus k squared psi. And this is the sort of little trick that people solving differential equations employ all the time. Knowing what the solution is, you can define a constant that makes a little more sense, in this case using a square for k instead of just some constant k. But in this circumstance, k is equal to root 2m times e over h bar. So this is our constant, which you just get from rearranging this equation. This equation you should recognize. This is the equation for a simple harmonic oscillator, a mass on a spring, for instance. Now, as I said before, the partial derivatives here don't really matter. We're only talking about one dimension, and we're talking about the time-independent Schrodinger equation, so the wave function here, psi, is just a function of x, not a function of x in time. So this is the ordinary differential equation that you're familiar with for things like masses on springs. And what you get is oscillation. Psi, as a function of x, is going to be a sine kx plus b cosine kx. And that's a general solution. A and b here are constants, to be determined by the actual scenario under which you're trying to solve this equation. This equation now, not the original Schrodinger equation. So these are our solutions. Sines and cosines. Sines and cosines. That's all well and good, but that doesn't actually tell us what the wave function is because, well, we don't know what A is, we don't know what B is, and we don't know what K is either. We know K in terms of the mass of the particle that we're concerned with, Planck's constant, and the E, separation constant, we got from deriving the time-independent Schrodinger equation. While that might be related to the energy, we don't know anything about these things. These are free parameters still. But we haven't used everything we know about the situation yet. In particular, we haven't used the boundary conditions. And one thing the boundary conditions here will determine is the form of our solution. Now, what do I mean by boundary conditions? Well, the boundary conditions are what you get from considering the actual domain of your solution and what you know about it, in particular at the edges. Now, we have a wave function that can only be non-zero between 0 and a. Outside that, it has to be 0. So we know right away our wave function is 0 here and 0 here. So whatever we get for those unknown constants, a, b, and k, it has to somehow obey this. We know a couple of things about the general form of the wave function. In particular, just from consideration of things like the Hamiltonian operator or the momentum operator, we know that the wave function itself, psi, must be continuous. We can't have wave functions that look like this. And the reason for that is this discontinuity here would do very strange things to any sort of physical operator that you could think of. For example, the momentum operator is defined as minus I h bar partial derivative with respect to x. The derivative with respect to x here would blow up, and we would get a very strange value for the momentum. That can cause problems. By sort of contradiction, then, the wave function itself must be continuous. We'll come back to talking about the boundary conditions on the wave function later on in this chapter, but for now, all we need to know is that the wave function is continuous. What that means is that since we're 0 here, we must go through 0 there, and we must go through 0 there, since we're 0 here. So, what that means, wrong color, means psi of 0 is equal to 0, and psi of A is equal to 0. What does that mean for our hypothetical solution, psi of x equals A sine kx plus B cosine kx? Well, first of all, consider this one. The wave function at 0 equals 0. When I plug 0 into this, the sine of 0, k times 0 is going to be 0. The sine of 0 is 0, but the cosine of 0 is 1. So what I'll get if I plug in 0 for psi is 1 times b. So I'll get b. Now if I'm going to get 0 here, that means b must be equal to 0. So we have no cosine solutions. No cosine part to our solutions. So everything here is going to start like sine. So it's going to start going up like that. That's not the whole story, though, because we also have to go through 0 when we go through A. So if I plug A into this, what I'm left with is psi of A is equal to capital A times the sine of Ka. If this is going to be equal to 0, then I know something about Ka. In particular, the sine function goes through 0 for particular values of particular values of its argument. Sine of x is 0 for x equals integer multiples of pi. What that actually looks like on our plot here is things like this. Our wave functions are going to end up looking like this. So let me spell that out in a little more detail. Our psi of A wave function is A times the sine of K times A. And if this is going to be equal to 0, Ka has to be either 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. This is just coming from all of the places where the sign of something crosses 0, crosses the axis. Now it turns out this is not interesting. This means psi is 0 everywhere, since the sine of 0 is, well, sine k times a. If Ka is going to be 0, then everything. If Ka is 0, k is 0. So the sine of k times x is going to be 0 everywhere. So that's not interesting. This is not a wave function that we can work with. Another fact here is that these plus or minuses, the sine of minus x is equal to minus the sine of x. Sine is an odd function. Since what we're looking at here has a normalization constant out front, we don't necessarily care whether there's a plus or a minus sign coming from the sine itself. We can absorb that into the normalization constant. So, essentially what we're working with then is that Ka equals pi, 2 pi, 3 pi, etc., which I'll just write as n times pi. Now, if k times a is going to equal n times pi, we can figure out what, well, let's just substitute in for k. which we had a few slides ago, was root 2m capital E over h bar. So that's k. K times a is equal to n pi. This is interesting. We now have integers coming from n here as part of our solution. So we're no longer completely free. We in fact have a discrete set of values. Now a, that's a property of the system. We're not going to solve for that. M, that's a property of the system. H bar, that's a physical constant. The only thing we can really solve for here is E. So let's figure out what that tells us about E. And if you solve this for E, you end up with n squared pi squared h bar squared over 2m a squared. This is a discrete set of allowed energies. I keep talking about solutions to the time-independent Schrödinger equation and how they have nice mathematical properties. What that actually means is, well, what I'm referring to are the orthogonality and completeness of solutions to the time-independent Schrödinger equation. What that actually means is the topic of this lecture. To recap, first of all, these are what our stationary states look like for the infinite square well potential. This is the potential such that v of x is infinity if x is less than 0 or x is greater than a, and 0 for x in between 0 and a. So if this is our potential, you express the time-independent Schrödinger equation, you solve it, you get sine functions for your solutions. You properly apply the boundary conditions, namely that psi has to go to 0 at the ends of the interval because the potential goes to infinity there. And you get n pi over a times x as your argument to the sine functions. And you normalize them properly, you get a square root of 2 over a out front. The energies associated with these wave functions, and this energy now is the separation constant in the conversion from the time-dependent Schrödinger equation to time-independent Schrödinger equation, are proportional to n, that index. The wave functions themselves look like sine functions, and they have an integer number of half wavelengths, or half cycles, in between 0 and a. So this orange curve, this is n equals 1. The blue curve is n equals 2. The purple curve is n equals 3. And the green curve is n equals 4. If you calculate the squared magnitude of the wave functions, they look like this. 1 hump for n equals 1. 2 humps for the blue curve, n equals 2. 3 humps for the purple curve, n equals 3. And 4 humps for the green curve, n equals 4. So you can see just by looking at these wave functions that there's a lot of symmetry. One thing we talked about in class is that these wave functions are either even or odd about the middle of the box, and this is a consequence of the potential being an even function about the middle of the box. If I draw a coordinate system here, going between 0 and a, either the wave functions have a maximum or they have a 0 at the middle of the box. So for n equals 1, we have a maximum. For n equals 2, we have a 0. And this pattern continues. The number of nodes is another property that we can think about. And this is the number of points where the wave function goes to 0. For instance, the blue curve here for n equals 2 has 1 node. This trend continues as well. If I have a wave function that, for instance, let me draw it in some absurd color, has 1, 2, 3, 4, 5, 6, 7 nodes, you know this would be for n equals 8. This would be sort of like the wave function for n equals 8. These symmetry properties are nice. They help you understand what the wave function looks like, but they don't really help you calculate. What helps you calculate are the orthogonality and completeness of these wave functions. So what does it mean for two functions to be orthogonal? Let's reason at this from a perspective which you're more familiar, the orthogonality of vectors. We say two vectors are orthogonal if they're at 90 degrees to each other, for instance. So if I had a two-dimensional coordinate system, and one vector pointing in this direction, let's call that A, and another vector pointing in this direction, let's call that B, I would say those two vectors are orthogonal if they have a 90-degree angle separating them. Now that's all well and good in 2 dimensions. It gets a little harder to visualize in 3 dimensions, and, well, what does it mean for two vectors to be separated by 90 degrees if you're talking about a 17-dimensional space? In higher dimensions like that, it's more convenient to define orthogonality in terms of the dot product. And we say two vectors are orthogonal in that case if the dot product of those two vectors is 0. Now in 2 dimensions, you know the dot product is given by the x components of both vectors, ax times bx, plus the y component of those two vectors multiplied together, ay times by. If this is 0, we say these two vectors are orthogonal. In 3 dimensions, we can say plus az times bz. And if this is equal to 0, we say the vectors are orthogonal. And you can continue this, multiplying together like components, or same dimension of the components of vectors in each dimension, multiplying them together. a1, b1, a2, b2, a3, b3, a4, b4, all added up together. And if this number is 0, we say the vectors are orthogonal. We can extend this notion to functions. But what does it mean to multiply two functions like this? In the case of vectors, we were multiplying like components, both x components, both y components, both z components. In the case of functions, we can multiply both functions' values at particular x coordinates and add all those up. And what that ends up looking like is an integral. Say the integral of f of x, g of x, dx. So I'm scanning over all values of x instead of scanning over all dimensions, and I'm multiplying the function values at each individual point, at each individual x, together, and adding them all up, instead of multiplying the components of each vector together at each individual dimension and adding them all up. The overall concept is the same, and you can think about this as, in some sense, a dot product of two functions. Now, in quantum mechanics, since we're working with complex functions, it turns out that we need to put a complex conjugate here on f in order for things to make sense. This should start to look familiar now. You've seen expressions like the integral of psi star of x times psi of x dx is equal to 1, our normalization condition. This is essentially the dot product of psi with itself. Psi, of course, is not orthogonal to itself, but it is possible to make a pair of functions that are orthogonal. And we say functions are orthogonal if orthogonal. So, we've been working with solutions to the time-independent Schrödinger equation for the infinite square well potential, the particle in a box case. How do these things actually work, though? In order to give you guys a better feel for what the solutions actually look like and how they behave, I'd like to do some examples and use a simulation tool to show you what the time evolution of the Schrödinger equation in this potential actually looks like. So, the general procedure that we've followed or will be following in this lecture is, once we've solved the time-independent Schrödinger equation, we get the form of the stationary states. Knowing the boundary conditions, we get the actual stationary states, the stationary state wave functions and their energies. These can then be normalized to get true stationary state wave functions that we can actually use. These stationary state wave functions will, for the most part, form an orthonormal set, psi sub n of x. We can add the time part, knowing the time-dependent Schrödinger equation, or the time part that we got when we separated variables in the time-dependent Schrödinger equation. We can then express our initial conditions as a sum of these stationary state wave functions, and use this sum then to determine the behavior of the system. So what does that actually look like in the real world? Not like very much, unfortunately, because the infinite square well potential is not very realistic, but a lot of the features that we'll see in this sort of potential will appear in more realistic potentials as well. So, this is our example. These are our stationary state wave functions. This is what we got from the solution to the time-independent Schrodinger equation. This was the form of the stationary states, these were the energies, and then this was the normalized solution with the time dependence added back on, since the time dependence is basically trivial. The initial conditions that I'd like to consider in this lecture are the wave function evaluated at 0 is either 0 if you're outside the, this should be A. If you're outside the domain, you're 0. If you're inside the domain, you have this properly normalized wave function. We have an absolute value in this, which means this is a little difficult to work with. But what the plot actually looks like, if I draw a coordinate system here, going from 0 to A, is this. It's just a tent, a properly built tent with straight walls going up to a nice peak in the middle. Our general procedure suggests that we express this initial condition in terms of these stationary states with their time dependence, and that will tell us everything we need to know. One thing that will make this a little easier to work with is getting rid of the absolute values we have here. So let's express psi of x time t equals 0 as a three-part function. First, we have root 3 over a, 1 minus. Now what we should substitute in here is what we get if, say, 0 is less than x is less than a over 2. Sort of the first half interval going out to a over 2 here. In this case, we have something sloping upwards, which is going to end up, in this context, being 1 minus a over 2 minus x over a over 2. So, to say another word or two about that, if x is less than a over 2, this quantity here will be negative. So I can get rid of the absolute value if I know that this quantity in the numerator is positive. So I multiply the quantity in the numerator by a minus sign, which I can express more easily just by writing it as a over 2 minus x. A over 2 minus x. That will then ensure that this term here is positive for x's in this range. 1 minus that is then this term in our wave function. For the other half of the range, root 3 over a, 1 minus something, and this is now from a over 2 is less than x is less than a, the second half of the interval. For the second half of the interval, x is larger than a over 2, so x minus a over 2 is positive. So I can take care of this absolute value just by leaving it as x minus a over 2. I don't need to worry about the absolute value in this range. So this is x minus a over 2 all over a over 2. And of course, if we're outside that, we get 0. This technique of splitting up absolute values into separate ranges makes the integrals a little easier to express and a little easier to think about. So that is our initial conditions. How can we express these initial conditions as a sum of stationary state wave functions evaluated at time t equals 0? This is where Fourier's trick comes in. If I want to express my initial conditions as a sum of stationary state wave functions, I know I can use this sort of an expression. This is now my initial conditions, and my stationary state wave functions are being left multiplied, complex conjugated, integrated over the domain, and that gives us our constants, C sub n, that go in this expression for the initial conditions in terms of the stationary state wave functions. The notation here is that if psi appears without a subscript, that's our initial condition. That's our actual wave function. And if psi appears with a subscript, it's a stationary state wave function. So what does this actually look like? Well, we know what these functions are. First of all, we know that this function, which has an absolute value in it, is best expressed if we split it up in two. So we're going to split this integral up into one going from 0 to a over 2 and one going from 0 to a. So let's do that. We have c sub n equals the integral from 0 to a over 2 of our normalized stationary state wave function, which is root 2 over a times the sine of n pi x over a. That's this psi sub n star, evaluated at time t equals 0. I'm ignoring time for now, so even if I had my time parts in there, I would be evaluating e to the 0, where time is 0. So I would get 1 from those parts. Then you have psi, our initial conditions, and our initial conditions for the first half of our interval was root 3 over a, 1 minus a over 2 minus x over a over 2. And I'm integrating that dx. The second half of my integral from a over 2 to a, looks much the same. Root 2 over a sine n pi x over a. That part doesn't change. The only part that changes is the fact that we're dealing with the second half of the interval, so the absolute value gives me a minus sign up here more or less. Root 3 over a, 1 minus x minus a over 2 over a over 2 dx. So, substitute in for n and do the integrals. This, as you can imagine, is kind of a pain in the butt. So what I'd like to do at this point is give you a demonstration of one way that you can do these integrals without really having to think all that hard. And that's doing them on the computer. You can of course use Wolfram Alpha to do these. You can of course use Mathematica. But the tool that I would like to demonstrate is called Sage. Sage is different than Wolfram Alpha and Mathematica in that Sage is entirely open source and it's entirely freely available. You can download a copy, install it on your computer, and work with it whenever you want. It's a very powerful piece of software. Unfortunately, it's not as good as the commercial alternatives, of course, but it can potentially save you a couple $100. The interface to this software that I'm using is their notebook webpage. So you can use your Google account to log into this notebook page, and then you have access to this sort of an interface. So, if I scroll down a little bit here, I'm going to start defining the problem. A, here, that's our domain. Our domain goes from 0 to a. H bar, I'm defining to be equal to 1, since that number is a whole lot more convenient than 10 to the minus 31st. N, x, and t, those are just variables. I'm defining them as variables given by these strings, n, x, and t. Now we get into the physics. The energy, that's a function of what index you have, what your which particular stationary state you're talking about. This would be psi sub n. This would be E sub n. E sub n is equal to n squared pi squared h bar squared over 2m a squared. That's an equation that we've derived. Psi of x and t, psi sub n of x and t in particular, is given by this. It's square root of 2 over a times this sine function times this complex exponential, which now uses the energy, which I just defined here. Psi star is the complex conjugate of psi, which I've just done by hand by removing the minus sign here. More or less just a copy-paste. G of x is what I've defined the initial conditions to be, which is square root of 3 over a times this 1 minus absolute value expression. And C sub n here, that's the integral of g of x times psi from 0 to a over 2 plus g of x times psi going from a over 2 to a. That's all well and good. Now I've left off the psi stars, but since I'm evaluating at time t equals 0, it doesn't matter. Psi is equal to psi star at t equals 0. I did have to split up the integral from 0 to a over 2 and a over 2 to a, because otherwise Sage got a little too complicated in terms of what it thought the integral should be. But given all this, I can plot, for instance, g, and if I click evaluate here, momentarily a plot appears. And this is the plot of g of x as a function of x. Now I defined a to be equal to 1, so we're just going from 0 to 1. This is that 10th function I mentioned. If I scroll down a little bit, we can evaluate c of n. This is what you would get if you plugged in to that integral that I just wrote on the last slide. You can make a list evaluating c of n for x going from 1 to 10, and this is what you get. You get these sorts of expressions. 4 times square root of 6 over pi squared, or minus 4 root 6 over pi squared divided by 9, 4 root 6 over pi squared over 25, 4 root 6 over pi squared over 49. You can see the sort of pattern that we're working with. Some number divided by an odd number raised to the nth power, or squared. We can approximate these things just to get a feel for what the numbers are actually like. And we have 0.99 minus 0.11 plus 0.039, etc. Moving on down. So that's the sort of thing that we can do relatively easily with Sage. Get these types of integral expressions and their values. You can see I've done more with this Sage notebook, and we'll come back to it in a moment. But for now, these are the sorts of expressions that you get for C sub n. So our demo with Sage tells us C sub n equals some messy expression. And it can evaluate that messy expression and tell us what we need to know. Now, the actual form of the evaluated C sub n was not actually all that complicated. And if we truncate our sum, instead of summing from, now this is expressing psi of x t, our wave function, as an infinite sum, n equals 1 to infinity, of C sub n psi sub n of x and t. If I truncate this sum at, say, n equals 3, I'll just have a term from psi 1 and psi 3. Recall back from the Sage results that psi 2, the coefficient of psi 2, C sub 2, was equal to 0. So let's find the expectation of x squared. Knowing the form of these functions, and now knowing the values of these C sub n from Sage, you can write out what x squared should be. This is the expected value of x squared, and it's going to be an integral of these numbers, 4 root 6 over pi squared times psi 1, which was root 2 over a sine, not n. So we're just dealing with psi 1 now. We have pi x over a. We have to include the time dependence now, since I'm looking for the expected value of x squared as a function of time now. And we have e to the, where'd it go, minus I times pi squared h bar squared t over 2ma squared, all divided by h bar, or I could just cancel out one of the h bars here. That's our first term, in our first term of our expression. The next term, we have 4 root 6 over 9 pi squared from this coefficient. Now psi 3 is root 2 over a sine of 3 pi x over a times, again, complex exponential, e to the minus I pi squared h bar squared t over 9 pi squared h bar squared t over 2ma squared, all divided by h bar. Now, what is this? This whole thing needs to be complex conjugated, because this is psi star. What's next? Well, I need to multiply this by x squared, and I need to multiply that by the same sort of thing, e to the plus this minus same sort of thing, e to the plus this. So this is the term in orange brackets here is psi star. This is our x. The term in blue brackets here is our psi. So we're just using the same sort of expression, only you can only see just how messy it is. This is the integral of psi star x squared psi. This is psi star, this is x squared, and this stuff is psi. We have to integrate all of this dx from 0 to a. This is pretty messy as well. Messy, but doable. Now, since I was working with Sage anyway, I thought, let's see how the time dependence in this expression plays out in Sage. So, going back to Sage, we know these C sub n's, these are the C sub n's that I chose for C sub 1 and C sub 3. And C sub n of x gives me some digits. Or, sorry, C sub n evaluated gave me these numbers in just in decimal form. Now I can use these C sub n's to express that test function where I truncated my sum at psi sub 3. So this is our test function. And if you evaluate it, it's a lot more simple when you plug in the numbers, sine 3 pi x and sine pi x. When h bar is 1 and a is 1, these expressions are a lot easier to work with, which gives you a feeling for why quantum mechanics often we assign h bar equal to 1. The expected value of x squared here is then the integral of the conjugate of my test function times x squared times my test function, integrated from 0 to a. And Sage can do that integral. It just gives you this. Sage can also plot what you get as a result. Now you notice Sage has left complex exponentials in here. If you take this expression and manually simplify it, you can turn this into something with just a cosine. There is no complex part to this expression. But Sage isn't smart enough to do that numerically, so I have to take the absolute value of this expression to make the complex parts, the tiny, tiny complex parts, go away. And if I plot it over some reasonable range, this is what it looks like. It's a sinusoid, or a cosinusoid actually. And what we're looking at here on the y-axis is the expected value of x squared. This is related to the variance in x. So it's a measure of more or less the uncertainty in position. So our uncertainty in position is oscillating with time. What does this actually look like in the context of the wave function? Well, the wave function itself is going to be a sum, c sub 1 times psi 1, c sub 3 times psi 3, c sub 5 times psi 5, c sub 7 times psi 7, etc. I can do that in general by making this definition of a function where I just add up all of the c sub n's and all the psi sub n's for n in some range. F of x, if I go out to 7, looks like this. You can get a feel for what it would look like if I added more terms as well. Now the plot that I'm showing you here is a combination of 4 things. First, it's the initial conditions shown in red. That's the curve that's underneath here, the tent. And I'm also showing you this approximate wave function when I truncate the sum at 2, just the first term. That's this poor approximation here, smooth curve. The function, if I truncate the approximation at 4, that will include psi 1 and psi 3. That's this slightly better approximation here, this one. And if I continue all the way up to 20, that's this quite good approximation, the blue curve here, that comes almost all the way up to the peak of the tent. So that's what our approximate wave functions look like, but these are all evaluated at t equals 0. What does that look like, for instance, in terms of the probability density and as a function of time? So let's define the probability density, rho of xt, as the absolute value of our approximate function, and I'll carry the approximation all the way to n equals 20, absolute value squared. And I'm getting the approximate form with this dot n at the end. So this is our approximate form of the probability density calculated with the first 20 stationary state wave functions. This plot then shows you what that time dependence looks like. I'm plotting the probability density at time t equals 0, probability density at time t 0.04, 0.08, 0.12, 0.16. We start with blue, dark blue. That's this sort of peaked curve, which should be more or less what you expect, because we did a problem like this for this sort of wave function in class. Then you go to dark green, which is under here, underneath the yellow. It seems to have lost the peak, and it's spread out slightly. Red is at time 0.08, and if I scroll back up to our uncertainty as a function of time plot, 0.08 is here. So it's pretty close to the maximum uncertainty. You expect the uncertainty, the width, to start decreasing thereafter. If I scroll back down here, this red curve then is more or less as wide as this distribution will ever get. And if we continue on in time, now going to 0.12, that was the orange curve here. And the orange curve is back on top of the green curve. The wave function has effectively gotten narrower again. And if you keep going all the way up to 0.16, you get the cyan curve, the light blue curve, which is more or less back on top of the dark blue curve. So the wave function sort of spilled outwards and then sloshed back inwards. You can sort of imagine this as ripples in a tank of water radiating out and then coming back to the center. This is what the time evolution would look like as calculated in SAGE. You can make definitions of functions like this, you can evaluate them, you can plot them, and you can do all of that relatively easily. Now I'll give you all a handout of this worksheet so that you get a feel for the syntax. If you're interested in learning more about SAGE, please ask me some questions. I think SAGE is a great tool, and I think it has a promising future, especially in education like this. For students, the fact that this is free is a big deal. So that's what the time variability looks like. We had our wave function, which started out sort of sharply peaked, our probability density, rho of x, which I should actually write as rho of x and t, which sort of got wider and then sloshed back in. So we sort of had this outwards motion followed by inwards motion, where our expectation of x squared, related to our uncertainty, oscillated. Oh, sorry. It didn't oscillate about x equals 0. It oscillated about some larger value. Sorry, it didn't oscillate about 0. It oscillated about some larger value. So there's some sort of mean uncertainty here. Sometimes you have less uncertainty, sometimes you have more uncertainty. That's the sort of time dependence you get from quantum mechanical systems. To get an even better feel for what the time variability looks like, there's a simulation that I'd like to show you. And this comes from Falstad.com, which, as far as I can tell, is a guy who was sick of not being able to visualize these things, so he wrote a lot of software to help him visualize them. So here's the simulation. And I've simplified the display a little bit to make things easier to understand. These circles on the bottom here, each circle represents a stationary state wave function. And he has gone all the way up to stationary state wave functions that oscillate very rapidly, in this case. But this is our ground state. This is our first excited state, second excited state, third excited state, etc. N equals 1, 2, 3, 4, 5, 6, 7, etc. Now, in each of these circles, there may or may not be a line. The length of the line represents the magnitude of the time part of the evolution of that particular stationary state. And the angle going around the circle here represents the phase as that evolution proceeds. So if I unstop this simulation, you can see this slowly rotating around. You're also probably noticing the color here changing. The color of this represents the phase. The vertical size of this represents the probability density, and the color represents the phase. So it's a representation of where you're likely to find it, and a sort of color-based representation of how quickly it's evolving. The vertical red line here in the center tells you what the expectation value for position is. And in this case, it's right down the middle. If I freeze this simulation and add a second wave function, this is now adding some component of the first excited state. And by moving my mice around here, I can add varying amounts, either adding none or a lot, and I can add it at various phases. I'm going to add a lot of it, an equal amount as the ground state, and I'm going to do it at the same phase. And I'm going to release and let that evolve. So you can see now the probability density is sort of sloshing to the left and sloshing back to the right. And if you look at our amplitude and phases, you can see the ground state is still rotating. The first excited state is rotating, but the first excited state is rotating 4 times faster. So when they align, you have something on the right. When they anti-align, something on the left. They're aligned, they're anti-aligned. And this sloshing back and forth is one way where we can actually get motion out of stationary states. You notice the phase is no longer constant. You have some red parts, some purple parts, and things are sort of moving around in an awkward way. The colors are hard to read, but you know now that the phase of your wave function is no longer going to be constant as a function of position. So those exponential time parts may be giving you a wave function that's purely real here and purely imaginary here, or some combination of purely real and imaginary, some general complex number. And that complex number is not simply e to the I omega t. It's e to the I omega something that's a function of position as well as time. It's complicated. I can, of course, add some more wave functions here, and you get even more complicated sorts of evolution. Our expected value of x is now bouncing around fairly erratically. Our phase is bouncing around even more erratically. But what we're looking at here is just the sum of the first 1, 2, 3, 4, 5, 6 stationary states, each evolving with the same amplitude and different phases. Now I'm going to stop the simulation and clear it now. Another thing I can do with this simulation tool is put a Gaussian into the system. So I'm going to put a Gaussian in here. So this is sort of our initial conditions, and the simulation has automatically figured out, well, I want this much, I want a lot of the ground state, psi 1, a lot of psi 3, a lot of psi 5, a lot of psi 7, a little bit of psi 9, a little bit of psi 11, etc. And if I play this, I'm going to slow this down a little bit first. If I play this, you see the wave function gets wide, becomes 2, gets narrower again, and sloshes back where it started. If you watch these arrows down here, you can tell when it comes back together, the arrows are all pointing in the same direction, and when it's dispersed, the arrows are sort of pointing in opposite directions. Since our initial conditions were symmetric, there's no reason to expect the expected value to ever be non-zero, ever move away from the center of this well. But as your, say, psi 1, psi 3, psi 5, psi 7, etc., oscillate at their own rates in time, the superposition results in a relatively complicated dynamics for the overall probability density. And of course, I can make some ridiculously wacky initial conditions that just sort of oscillate all over the place in a very complicated way. There are a lot of contributions to this wave function now, and no one contribution is particularly winning, but you can occasionally see little flashes of order in the wave function. I highly encourage you to play with these simulations just to get a feel for how time evolution in the Schrödinger equation works. There are a lot more than just the square well here. There's a finite well, harmonic oscillator, a pair of wells. There are lots of things to play with, so you can get a reasonably good feel with how the Schrödinger equation behaves in a variety of physical circumstances. So that's our simulation, and hopefully you have a better feel now for what solutions to the Schrödinger equation actually look like. To check your understanding, explain how these two facts are related. Time variability in quantum mechanics happens at frequencies given by differences of energies, whereas in classical physics, you can set the reference level for potential energy to whatever you want, sort of equivalent to saying, I'm measuring gravitational potential from ground level versus from the bottom of this well. The system we're considering in this lecture is the quantum harmonic oscillator. There are a few ways to solve the Schrödinger equation for the quantum harmonic oscillator, but what we're going to do in this lecture is a solution more or less by pure cleverness. The solution is called the solution by ladder operators, and we'll see what that means in a few minutes. Just to set the stage, the potential that we're working with here is the potential of a harmonic oscillator. The amount of energy, essentially, that you get if you displace a particle attached to a spring from equilibrium. If you remember spring potential energy, the potential as a function of x is 1/2 the spring constant times the displacement x squared. But it's traditional to write this instead in terms of the angular frequency. The angular frequency of the oscillations that result when a mass m is on a spring with spring constant k is the square root of the spring constant divided by the mass of the particle. And if you substitute this in here and mess around with the simplification a little bit, you end up with 1/2 m omega squared x squared. So this is the form of the potential that we'll be using. What this looks like, if I plot it, is a parabola. Not the world's prettiest parabola, but you get the idea. And we know a little bit about what solutions to the Schrodinger equation should look like under circumstances like this. Let me draw this a little lower so I have room. If I have some energy E in this combined energy wave function axis, making a diagram of what the wave function looks like, if I start my wave function here, you know in this region the energy is above the potential, so the Schrodinger equation solutions have to curve downwards. And what they end up looking like is, well, something like this, say. Now, in the regions outside here, where the potential is above the energy, the Schrodinger equation solutions curve upwards. In the case of the harmonic oscillator solutions, they curve just down to kiss the axis. And you end up with a nice sort of hump-shaped wave function. If you have a higher energy, say up here, it's entirely possible to get solutions that look different. Suppose I started my wave function here, pointed at some angle. The energy now is higher relative to the potential, so the wave function is going to curve more, and it's possible to make it curve down to the point where when it reaches this point now where the potential is higher than the energy and it starts curving back upward, you again get a wave function that just smoothly joins in with the axis, giving you a sort of nice normalizable wave function. So these are the sorts of solutions that we expect to get. If you want to get these solutions just by, well, like drawing them, like I just did, you can conceptually understand what they look like, but quantitatively you'll have to do a lot of fine-tuning to get these energy levels exactly right and to get the initial conditions here. I just started my wave function. How high up should I start my wave function? Or in this case, should I start it at the middle? Should I displace it? What should this angle here be? Fine-tuning like that is hard, and we'll see how to do that in the next lecture. But in this case, we're going to make a solution by cleverness instead of fine-tuning. To set that up, let's go back to the time-independent Schrodinger equation. This is the general time-independent Schrodinger equation, where now we're going to be substituting in the harmonic oscillator potential, 1/2 m omega squared x squared. That means the harmonic oscillator time-independent Schrodinger equation that we actually have to work with minus h bar squared over 2m times partial derivative of psi with respect to x squared plus 1/2 m omega squared x squared psi is equal to E psi. So this here is the Hamiltonian operator. The time-independent Schrodinger equation is also often just written as h psi equals E psi, and that's fine. Let's take a closer look at this Hamiltonian operator. Maybe we can do something with it. The cleverness comes in this step. Consider factoring the Hamiltonian. Well, I can simplify this a little bit by pulling out, for instance, a 2m here, and writing this as the momentum operator squared. This is essentially p squared over 2m, the kinetic energy part. This is the potential energy part. If I pull out 1 over 2m, what I get, 1 over 2m, p hat squared plus m omega x, quantity squared. This is suggestive. If we had numbers, and I had something like a squared plus b squared, I could factor that over the complex numbers as ia plus b times minus ia plus b. If you expand this out, you'll end up getting a plus a squared from multiplying these, a plus b from multiplying these, and similar to the cross terms in, say, a minus b times a plus b, the cross terms end up canceling out, and we would end up with what we started. Now, this is suggestive. You can't actually factor operators like this because they're not numbers, they're operators, and operators don't necessarily behave the same way numbers behave. We'll see what that means in a minute, but for now, let's just suggest looking at things like this. Plus or minus I times the momentum operator plus m omega x, where x now is the position operator. Now x, the position operator, just entails multiplying by x, so perhaps I should put a hat here, perhaps I shouldn't. Doesn't really matter. This is what we're considering now. I haven't justified this in any way beyond saying it kind of looks like maybe it would factor. Well, does it factor? These things are called ladder operators, and they're traditionally defined, just to make the notation a little bit simpler, a hat, and there's either a plus or a minus on this. Let me draw this a little bigger. A hat, plus or minus in the subscript, and these are defined to be 1 over the square root of 2 h bar m omega. The constant just makes things more nice overall, times minus or plus I p hat plus m omega x. This is now the position operator x hat. So this is the traditional definition. Let's see. If we have something that properly factors, what we should have is that a hat minus times a hat plus is our Hamiltonian. Is this true? This is an operator algebra problem, and operator algebra problems are tricky to do without test functions, but initially we can just write this out. We have two a's being multiplied together, so we're going to have a 1 over 2 h bar m omega out front, and then we're going to have I p hat plus m omega x times minus I p hat plus m omega x. Once again, hats on the x's if you prefer. So far, we've just written down our operators in order. Now, if I actually tried to expand these out, 1 over 2 h bar m omega. Now, this term, I times minus I, that's just plus 1. So we would get p hat squared. So far, so good. For this term, this is okay as well, plus m squared omega squared x hat squared. That's still okay. We're still on track. This was more or less what our Hamiltonian looked like. The cross terms get a little more interesting, though. We have a term like this, which gives us, let's see, we're going to end up with a minus I from this, minus I m omega, and we have x hat p hat. We're going to end up with something very similar from this term. We're going to have an I, we're going to have an m, we're going to have an omega, except in this case we're going to have p hat x hat, not x hat p hat, as we had here. So I'm going to factor the constants out and do that in the right color. That means we're going to have minus p hat x hat here. So this is what we get when we expand this out. This part here looks a lot like the Hamiltonian. So we're on the right track. It's actually like 1 over h bar omega times the Hamiltonian. This part, though, this is a little more difficult to work with. And it turns out that this piece right here, this sort of thing appears a lot in quantum mechanics, and we have a name for it and a notation for it. And the notation is x hat comma p hat in square brackets. This is called a commutator. And fundamentally, the fact that I can't just subtract these two things from each other and get 0 is one of the most fundamental parts of quantum mechanics, one of the most fundamental features of quantum mechanics. So, let's talk about commutators in a little more detail. The commutator in general is defined for two operators A and B to be what you just saw on the last page. First, I have A, B, and then I subtract the opposite order, B, A. So if I acted on this, or if I used this operator, this combined operator, to act on a wave function, I would first let A act and then let B act. And I would subtract that from what I get if I let B act and then A act. Just to make that a little more explicit, if I had A, B minus B, A acting on some wave function, I would say that's A, B, psi minus B, A, psi. You don't necessarily get the same answer for both of these things because the order in which operators act is important. So let's look then at our commutator. The commutator we had in the last slide was x and p. The commutator of x and p is x hat p hat minus p hat x hat. And let's allow this to act on some wave function psi. In order to make my notation correct, I ought to have the same sort of psi here. So if I allow this to act on psi, first we're going to have x hat p hat psi minus p hat x hat psi. And what this means is x hat is acting on p hat acting on psi, and this is p hat acting on x hat acting on psi. We have definitions for these things. X hat is just x multiplied by something, and p hat is minus I h bar times the derivative of something, in this case, psi. Our second term here is minus I h bar times the derivative of, with respect to x, of x times psi. When I apply the derivative here, I have to use the product rule since I have a product of two terms. I'll have to hit x in one term and psi in the other term. So, the leftmost term here is easy to deal with, though. It's just minus I h bar x d psi dx. Actually, let's factor out a minus I h bar from both terms, since they both have it. So x d psi dx is my first term here. Then I have minus, if I use the derivative on the x, derivative of x with respect to x is just 1. So all I'll be left with is the psi remaining untouched in the product rule. And if I let the derivative hit the psi, I'll leave the x untouched, and I'll have the derivative of psi with respect to x. This is good because here I have an x d psi dx minus x d psi dx. So I can let these terms subtract out and cancel. And what I'm left with, I have a minus I h bar times minus psi, which is just going to be I h bar psi. So I started with the commutator acting on the wave function, and I just got constant multiplied by the wave function. So I can drop my hypothetical wave function now and just write an equation involving the operators again. The commutator of x and p is I h bar. It's a weird looking equation, but you can see, if you recall from the last slide, what we're going to end up with. When we evaluated a minus hat, a plus hat, we ended up with 1 over h bar omega times the Hamiltonian, plus some constants. And if you flip back a slide, the IH bars end up actually canceling out, and we just end up with plus a half for our constant. So while we did not succeed in fully factoring the Hamiltonian, we did get the Hamiltonian back, plus a constant. And if you reverse the order and repeat the algebra, a hat plus a hat minus, you end up with the same sort of thing. It looks very similar. You get 1 over h bar omega times the Hamiltonian minus a half instead. What this means is we can express the Hamiltonian in terms of these ladder operators and these constants. What we get for the Hamiltonian, h hat, is h bar omega times a minus a plus operators minus a half. Or alternatively, the Hamiltonian is equal to h bar omega a plus a minus plus a half. So these are the sorts of things that we got from our operator algebra after attempting to factor the Hamiltonian. That was pretty clever, but it didn't actually get us a solution. It just got us a different expression of the problem. The cleverness really comes in considering ladder operators and energy. The time-independent Schrodinger equation here is h hat psi equals E psi. So suppose we have some solution psi to the Schrodinger equation. We can then express the Hamiltonian in terms of these ladder operators, h bar omega times a plus a minus operators plus 1/2 acting on the wave function should be equal to E times the wave function. The clever part is this. What if I consider h hat times a plus psi? What happens to the wave function if I allow a plus to act on it before I allow the Hamiltonian to act on it? Now, assuming this is the case, maybe we can manipulate our expressions here involving the Hamiltonian and the ladder operators to get something with which we can apply our solution. Let's see what happens. Expressing the Hamiltonian now as ladder operators, h bar omega a hat plus a hat minus plus 1/2 now acting on a plus hat psi. Forgot my hat there, sorry. Looking at this, you can take a plus psi and distribute it in to the expression in parentheses here. h bar omega a plus hat a minus hat a plus hat psi plus a half psi. Put another way, I'm really just distributing the operator in. And that's actually a more convenient way to look at it. So I'm going to erase my psi's here, and I'm going to leave my psi outside the expression. Oops, and I forgot an a plus hat here. Sorry about that. Just distributing the a plus in here, you'll end up with plus minus plus, and just plus on the 1/2. Now, you notice I have an a plus here, and an a plus here. If you think about factoring this out to the left, that's actually allowed as well. I can rewrite this as h bar omega a plus hat in front of the expression a minus hat a plus hat plus 1/2, all acting on psi. That's okay. What's nice about this is if you look, we have here now an h bar omega and an a minus a plus. If I had the appropriate constant here, which would turn out to be minus a half, I would have the Hamiltonian back. And getting the Hamiltonian back means we might be able to apply our Schrodinger equation. So let's rewrite this as h bar omega a plus half times a minus a plus minus a half plus 1. I haven't changed anything now, except this piece. This is my Hamiltonian. I had two expressions for the Hamiltonian that I got from calculating the product of ladder operators. One if I did a plus first and then a minus, one if I did a minus first and then a plus, and they were different by the sign that appeared here. So the fact that this is the Hamiltonian allows me to rewrite things a little bit. It turns out I can rewrite this whole expression as a plus hat acting on the Hamiltonian, and you have to distribute the h bar omega in, Hamiltonian operator plus h bar omega acting on psi. So I'm starting to lose my ladder operators, which is a good sign because I don't actually want expressions with lots of ladder operators in them. I'd like expressions with things that I know in them. And it turns out you know what happens when the Hamiltonian acts on psi. So if I distribute psi in here, I'll just have psi times h bar omega and the Hamiltonian acting on psi. But you know the Hamiltonian acting on psi is E times psi. So we're definitely making progress now. This is going to become A plus hat times E plus h bar omega psi. This now is all constant. So it doesn't matter if I put it in between the ladder operator and the wave function or not. So I can pull that out and make this E plus h bar omega times ladder operator A plus acting on the wave function psi. If I rewrite my entire equation then, I end up with h hat acting on ladder operator psi, A plus psi, is equal to E plus h bar omega ladder operator acting on psi, A plus acting on psi. This looks a lot like the Schrodinger equation for a wave function given by A plus psi. So, if psi is a solution to the time-independent Schrodinger equation, A plus psi is also a solution to the time-independent Schrodinger equation with this new energy. That's really the clever part. If psi is a solution, A plus psi is also a solution. That's really quite interesting. What that means is if I have one solution psi, I can apply the ladder operator, which I've just been writing as A plus hat here. But we know what the ladder operator A plus is. It's a combination of the momentum operator and multiplication by x with appropriate constants thrown in. We know about A plus psi. If we knew the wave function, we could actually do this. It would involve taking some derivatives and multiplying by some constants. We can do that. So this gives us some machinery for constructing solutions from other existing solutions. We haven't actually solved the system yet. There's a little bit of cleverness left. And this has to do with ladder operators and the ground state. What we showed on the last slide was that if psi was a solution, then A plus hat psi was a solution with energy E plus h bar omega. It turns out A minus hat psi, you can follow through the same algebra, is also a solution, but it has energy E minus h bar omega. So suppose we have some solution, psi, and I'll call it psi sub n now. If we apply the ladder operator, A plus psi, we'll end up with some wave function psi n plus 1. It's another solution to the Schrodinger equation. It has a slightly higher energy. The energy has been increased by the amount h bar omega here. I can repeat that process, and I'll get, say, something I would call psi n plus 2. And you can keep applying the ladder operator over and over and over, and you'll generate an infinite number of solutions with higher and higher and higher energies. We can also apply the ladder operator A minus hat, and you'll get something I'll call psi sub n minus 1 with slightly lower energy. The energy has been lowered by an amount h bar omega. You can apply the ladder operator A minus hat as many times as you want, of course, as well, and you'll get psi sub n minus 2, or psi sub n minus 3, or psi sub n minus 4, or psi sub n minus 5. Every time you apply the lowering operator, the ladder operator A minus hat, you get another solution with lower and lower and lower energy. But we know if we have a wave function with very, very low energy, it's going to behave very strangely. If your potential, for instance, is your harmonic oscillator potential, it looks like this, and your energy, E, is below your potential V of x, then if I start my wave function, say, anywhere, really, let's start it here. The fact that the energy is below the potential for the entire domain of the potential means that over the entire domain of the wave function is going to be curving away from the axis. The wave function is going to be blowing up. That's a problem. I cannot have solutions with arbitrarily low energy. What that means, cannot have solutions with very low energy. What that means is that if I apply this lowering operator over and over and over again, sooner or later I have to get something that I can no longer apply the lowering operator to. Something will no longer give me a meaningful solution. And it turns out the best way of thinking about that is there is some wave function such that A minus acting on that wave function is equal to 0. If we have a state like this, this will be our lowest energy state, and I'll call it psi sub 0. This is a necessary condition for getting a normalizable wave function. If we did not have this condition, we'd be able to keep applying the lowering operator, and we would sooner or later get solutions that were not allowed. That's a problem. So let's figure out what this actually implies. We know what the lowering operator is. We know what 0 is. We have to be able to solve this. This is going to be an ordinary differential equation just given by the definition of the ladder operator. 1 over 2m h bar omega in the square root times the momentum operator h bar d by dx plus m omega x acting on psi sub 0 is equal to 0. This we can solve. This is a relatively easy ordinary differential equation to solve, in fact, because it's actually separable. If you mess around with the constants, you can convert this into the differential equation d psi dx is equal to minus m omega over h bar x psi. And these are now psi zeros, sorry. This can be directly integrated. I can rewrite this as d psi over psi is equal to minus m omega over h bar x dx. And if I do this integral, integrating both sides of this equation, what you end up with, after you simplify, is that psi sub 0 is equal to e to the minus m omega over 2 h bar x squared. E to the minus x squared for our ground state, for our lowest energy psi sub 0, for our lowest energy solution. There's a normalization constant here, and I'll save you the trouble of calculating the normalization constant out. It's m omega over pi h bar to the 1/4 power. So this is our ground state. Now it's off to the races. By consideration of the Hamiltonian and attempting to factor it and defining ladder operators and exploring the consequences of these ladder operators, in particular that we ended up with any single solution giving us an infinite number of solutions by repeatedly applying a plus and a minus, the necessity of a normalizable wave function, the necessity of having a lowest energy state, meant that we got an equation that was simple enough that we could solve it with just simple ordinary differential equations. Now, there's really no such thing as a simple ordinary differential equation, but this was a lot easier to solve than some ordinary differential equations. What that ended up giving us in the end was psi 0, our lowest energy state. We can then apply the raising operator, a plus, over and over and over again to construct an infinite number of states. To summarize, here's a slide with all of the definitions. The raising and lowering operators, the ladder operators, a plus and a minus, the expressions that you get from simplifying the Hamiltonian in terms of the ladder operators. I want to highlight these two expressions because I have not completely derived them. I have argued that the ladder operator a plus applied to some wave function psi sub n gives you psi sub n plus 1, but I haven't told you anything about the normalization. You could apply this operator over and over again and renormalize all of the wave functions you get as a result, but it turns out there's a pattern to them, and that pattern is that what you get by applying the ladder operator a plus to psi n is not psi n plus 1, but psi n plus 1 times this square root of n plus 1. Likewise for the lowering operator. There's a nice explanation in the textbook of how you can use still more cleverness to derive what these normalization multiplicative factors are. Our ground state we got from applying the lowering operator to some hypothetical wave function, which when we solve it, we ended up with this, our psi sub 0, our lowest energy wave function. Putting all of this together, you can come up with an expression for the nth wave function, psi sub n, in terms of psi sub 0. You have to apply a plus n times. This superscript n here means to apply a plus n times. For instance, a plus hat cubed would be a plus, a plus, a plus, all acting on, say, if there's a psi in here, all acting on the psi, just one after the other. And if you calculate the energies that we get, applying the Hamiltonian to our lowest energy wave function, and then knowing that the raising the operator a plus gives you a new solution with an energy that's increased by the amount h bar omega, you end up with the energies. So we actually know everything about the solutions now. We know the lowest energy solution, we have a procedure for calculating higher energy solutions, and we know the energies of all of these solutions. So that's wonderfully good. To give an example of how these things are actually used, let's calculate psi 1. We know psi 1, writing black a little easier to read, psi 1 is going to be equal to a plus acting on psi 0, and there's that normalization constant, the square root of n plus 1, except in this case n is 0, so this is just going to be 1. If I substitute in the definition of the operator a plus, that's 1 over that square root of 2 h bar m omega minus I t hat plus m omega x, where p hat now is minus I h bar d by dx. This is my raising operator. That's all acting on psi sub 0, and we know psi sub 0, given in normalized form, m omega over pi h bar to the 1/4 power e to the minus m omega over 2 h bar x squared. We just have to evaluate this, taking derivatives of this exponential and multiplying it by x. So let's continue with that. Moving our normalization constant out front, m omega over pi h bar to the 1/4 power over this square root factor, 2 h bar m omega. Simplifying this expression out, we end up with minus h bar d by dx plus m omega x, all acting on e to the minus m omega over 2 h bar x squared. Now, this term with the m omega x, that's going to be easy. The derivative here is going to be relatively straightforward as well. And what we end up with is the constants we had out front, and taking the derivative of an exponential, we're just going to get the exponential back. So we're going to have an h bar e to the minus m omega over 2 h bar x squared times the inner derivative, the derivative of what's in the exponent itself, which is minus 2 x, sorry, let me actually write this out, minus m omega over 2 h bar times 2x. That's okay. The minus sign here and the minus sign I had out front will end up canceling out. I can simplify, I can cancel out my 2's, I can cancel out an h bar. That's all I'm going to do with that term for now. The other term is easy. M omega x e to the minus m omega over 2 h bar x squared. So that's our result. We have an e to the m minus m omega, etc., over x squared in both of these terms. Just going to pull that out to the right. And if I pull my constants out to the left, I have an m omega and an m omega in both of these terms, so I can factor that out. And what you end up with at the end, after all is said and done, the only step I'm skipping now is to simplify the constants. What you end up with is m omega over pi h bar to the 1/4 power. There isn't much we can do about that. Square root of 2m omega over h bar x e to the minus m omega over 2h bar x squared. Both of these terms had x and x in them. So these terms just add up, and this is what we end up with at the end. This is your expression for psi 1. The algebra here gets a little bit complicated, but fundamentally what we're doing is calculus, taking derivatives, multiplying, manipulating functions, applying the chain rule, and turning the crank, more or less. The formula we started with here does give us machinery that we can use to calculate any wave function that we might want as a solution to the time-independent Schrodinger equation for the quantum harmonic oscillator. To check your understanding, here is an operator algebra problem. Given that x hat is the position operator and t hat is the kinetic energy operator, essentially p squared over 2m, calculate the commutator of x and t. Now it's just defined as this. The one tip I have for you here is to be sure to include a test function when you expand out these terms, and when you take second derivatives, do it as a sequence of 2 steps. Don't just try and take the second derivative twice in one step. You may have to apply the product rule. We've heard about the solution to the harmonic oscillator time-independent Schrodinger equation by cleverness with ladder operators. This is the differential equation we have to work with is something that can be solved by other techniques. In particular, it can be solved by power series. Power series is a common solution technique for ordinary differential equations, so it's useful to see how it applies to the time-independent Schrodinger equation. The equation we have to solve is this. Essentially, H operator psi equals E psi, where we're now only talking about psi as a function of x. We have a second partial derivative with respect to x that comes from the kinetic energy part of the Hamiltonian operator, and we have a potential energy part here, where the potential function we're now working with, v of x, is the potential in a harmonic oscillator, 1/2 m omega squared x squared, basically proportional to the square of the displacement of a particle from some equilibrium position. Often, the first step in solving an ordinary differential equation like this is to make some change of variables to simplify the structure of the equation. Basically, what we're looking to do is get rid of some of these constants. And it turns out the change of variables that we want to use here, and you can determine this with a little bit of trial and error, knowing how change of variables works, is we want to, instead of x, we want to use x is the square root of h bar over m omega times some new coordinate phi. Now, what happens when we substitute in new coordinates here? Well, we have to worry about psi of x here, and here, and here. Psi is going to have to, in some sense, change a little bit in order to be represented as a function of psi instead of x. We also very clearly have an x here, and we have to worry about the second partial derivative with respect to x. So let's work through this step by step, and you'll see how these substitutions can be made. First of all, we can pretty easily handle these psi as a function of x, because we know what x is. X is the square root of h bar over m omega times psi. So we'll have minus h bar squared over 2m. Don't have to worry about the constants. Second derivative of psi, now square root of h bar over m omega psi is the argument for psi, but we're still second differentiating with respect to x. dx squared. Pardon me. Plus 1/2 m omega squared. Now substituting in for x, this is relatively easy. We're going to get this squared, h bar, over m omega c squared, times psi, and the argument of psi is again going to be this root h bar over m omega c, equals e times psi, where again the argument of psi is this function of c. You can see there's going to be some cancellation here. I can get rid of some m's and some omegas, but I'll leave that until later. The only difficult term to deal with here is the second partial derivative with respect to x of psi, which is now a function of xi. Now, when you're taking the derivative of something with respect to a function of something else, you have to use the product rule. Sorry, not the product rule, the chain rule. So I'm going to apply the chain rule to this derivative term, and I'm going to split it up into two steps, two first derivatives instead of one second derivative, just to see how each of those steps applies. So first of all, minus h bar squared over 2m times the derivative with respect to x of the derivative with respect to x of psi of xi. Now, I can take the derivative of psi with respect to xi. That I know how to do. That's just d psi d xi, because psi is a function of xi. But in order to turn this into a partial derivative with respect to x, I have to multiply by the derivative of xi with respect to x. So this is the chain rule at work here. And I know how to take the derivative of xi with respect to x, because I know xi is a function of x. This is just going to give me square root of m omega over h bar. What I get if I solve for xi and then just differentiate with respect to x. This can then be pulled out front. It's a constant, doesn't contribute anything. Minus h bar, oops, don't want to be an orange. Minus h bar squared over 2m times our constant, root m omega over h bar, times partial derivative again with respect to x. But now I'm taking the partial derivative of psi with respect to xi. So again, I have to apply the chain rule. What I'm going to get differentiating psi with respect to xi is a second derivative of psi with respect to xi now, times again a partial derivative of xi with respect to x. You can do this all in one step if you know that the partial derivative of xi with respect to x is simple. If the partial derivative of xi with respect to x had some problems in it, some dependence, you would have two separate functions here. You wouldn't be able to factor it out as a constant, and you have to apply the product rule to this term. So be careful when you're doing this. Don't just assume that you can take a second partial derivative with the chain rule in one step. But the second step here, again, partial derivative of xi with respect to x gives me the square root of m omega over h bar, which as a constant I can pull out front and combine. What I'm left with for this term then is minus h bar squared over 2m times m omega over h bar, again giving me some nice cancellations, times the second derivative of psi with respect to xi. So this converts my derivative with respect to x into a derivative with respect to xi. I've converted my x into xi, and all of my other x's into xi's just by changing the arguments of psi. So the overall equation I get now, minus h bar squared over 2m, m omega over h bar, second partial of psi with respect to xi, plus 1/2 m omega squared h bar over m omega, xi squared psi, equals e psi. This is good because we can do some cancellations. We can, for instance, cancel one of the omegas here, and we can cancel the m. We can also cancel an m here and one of the h bars. What's nice about this is I have h bar omega over 2 here and h bar omega over 2 here. So I have the same constant, and I'm going to move both of these constants, factor them out, move them over to e, to lump all of my constants together. I'm also going to change the ordering of the terms to get my two psi's together and mess with the signs a little bit. But the final equation you get is the second derivative of psi with respect to xi is equal to xi squared minus some constant k psi, where k is what we got when we aggregated all these constants together. It's, need an equal sign there, k is equal to 2e over h bar omega. So this is a differential equation that's substantially simpler than the differential equation we had here. Just by rearranging constants, we haven't actually changed the structure of the solution any. This differential equation isn't something that we want to just go ahead and try and solve with power series, though, and you'll see why in a moment. Solutions that are most easily represented by power series are solutions that are only interesting near the origin. And this equation tends to be difficult to represent with power series because of what happens for large values of c. So let's look for something called an asymptotic solution. Let's look for a solution for large c. C much, much greater than 1. What happens when c is much, much greater than 1? Well, if c is much, much greater than 1, I don't care about k here. It's going to be about equal to c squared. C squared minus k is about c squared. That means the actual differential equation we have to solve is second derivative of psi with respect to c is c squared psi. Oh, and I've unintentionally changed notation here. This is a derivative of psi, not a partial derivative of psi. That doesn't really matter. The partial derivative and the total derivative are the same because psi now is only a function of x. Likewise, I should also probably write capital psi here instead of lowercase psi. That's just an error. Apologies. This approximate equation has solutions. In the case of an asymptotic solution, we don't really care about the exact solution. An approximate solution is good enough if we can still use this approximation in our solution. So our approximate solution, and you can check this, is that the wave function is approximately equal to a times e to the minus c squared over 2 plus b e to the c squared over 2. Rewrite that, or make it more look like a c. So this equation is an approximate solution to this equation. And you can see that by taking the second partial derivative of psi. I'll just look at this term, for instance. The second partial derivative of this term, d squared dx, or dc squared of e to the minus c squared over 2 is, and you can plug this into whatever computational algebra tool you want, c squared minus 2 times e to the minus c squared over 2. So this, again, approximately, for large values of c, is going to be about equal to c squared. So second derivative of this effectively pulled down a c squared and gave us our function back. And that's what our approximate differential equation is. Now, if you had a minus sign in front of the c and the exponent here, you'd end up with much the same sort of expression. So you can see this is effectively an approximate solution to our approximate differential equation. This is useful in a couple of ways. First of all, there will be large values of c. Unlike the case of the infinite square well, there's no sound reason for believing that the wave function will go to 0 for large values of c. It's certainly not required by the laws of physics. It is, however, required by the laws of mathematics. In order to have a normalizable wave function, this asymptotic behavior can't have any of this in it. So if we want our wave function to be normalizable, then b must equal 0. That's a requirement. What that tells us then, if we have something that's going to be a solution to the time-independent Schrodinger equation, its asymptotic behavior will be given by this. So psi is approximately equal for large c to some constant e to the minus c squared over 2. That's an approximate solution. This is the story all about how the Schrodinger equation applies to the free particle. What do we mean by a free particle? Imagine an electron, for instance, floating in the vacuum of space. It never encounters anything. It never runs into anything. How that enters the Schrodinger equation is that there is effectively no potential anywhere. So the time-independent Schrodinger equation, and we're back to one dimension now, so don't think about a particle floating around in the vacuum of three-dimensional space. It's floating around in the vacuum of one-dimensional space. The left-hand side of our time-independent Schrodinger equation is the Hamiltonian operator applied to the wave function. This is in some sense the total energy, which breaks down into a kinetic energy component here with the momentum of the particle squared divided by twice the mass, and a potential energy part here, where V of x is the potential energy that the particle would have to be found at a particular location. In the context of the free particle, where there is no potential, what that means is that V of x is equal to 0 everywhere. That means we can just cross out this term entirely. We don't have to worry about it. What we're left with then for our time-independent Schrodinger equation is minus h bar squared over 2m times the second partial derivative of psi with respect to x equal to e psi. Now, we have some constants here, and we have a constant here, so let's lump them all together. And I'm going to shift the signs around a little bit as well, so that what we've got is the second derivative of psi with respect to x is equal to minus 2me over h bar squared times the wave function. So just lumped all our constants together and multiplied through by a minus sign. Now, you notice the second derivative here of the wave function, giving you the wave function back. The fact that we're taking a second derivative suggests that the constant here perhaps is squared. So what I'm actually going to write this as is the second derivative of psi with respect to x is equal to minus some constant k squared times the wave function, where k, our constant, is the square root of 2me over Planck's constant. So this is the differential equation, and we ought to be able to solve this. This is relatively simple compared to the structure of the differential equations we got from the harmonic oscillator. So how do we solve this? Well, what we have, second partial of psi with respect to x is minus some constant squared times the wave function. Taking the second derivative gives you a constant squared. That immediately suggests we look for exponential solutions. And it turns out the general solution to this equation is some constant times e to the minus I k x plus b e to the plus I k x. If I take the second derivative of this exponential term, I'll get a minus I k squared, which you know is just minus k squared, applying the rules of complex numbers, which is what we get here. So when I take the second derivative of this term, I'll end up with minus k squared times this term. And I get the same sort of thing here. If I take plus I k squared from the second derivative, that again gives me a minus k squared. So we're okay. This is our general solution. When we include time in this, since you know this is a solution to the time-independent Schrodinger equation, it's going to have time dependence given by the time part, the time equation that we got when we did separation of variables. What you end up with is psi of x and time now is equal to a e to the minus I k x times e to the I energy t over h bar plus b times e to the I k x e to the I energy time over h bar. And I've left off my minus signs here in the energy dependence, just conventional to include minus signs there. We can rewrite this a little bit as a e to the I k. Now, what I'm doing here is substituting in the definition of k, which if you remember was the square root of 2me all over h bar, expressing energy in terms of this k. And when I do that, what I end up with is this term ends up looking like h bar k squared over 2m. Substituting that in here is what we get from manipulating our constants here. If I do that manipulation, the first term here, instead of having this product of two exponentials, I'm going to write it as a sum in the exponent, x minus h bar k over 2m t plus b times something that looks very similar, e to the minus I k x plus h bar k over 2m t. So these are our general solutions to the full Schrodinger equation. Our full wave function is a function of both position and time. And these solutions are traveling waves. You can think about this as a traveling wave in the context of looking at this as a complex number. If I look at e to the I kx, for instance, as a function of x, you know what that does in the complex plane. It just rotates around in the complex plane. If I look at this as e to the I kx, let me redo that a little. I k times x minus h bar k over 2m t. And I treat this as a function of time. Again, we just get rotation in the complex plane. We get rotation in the other. I promised in the last lecture that the solutions we got to the time-independent Schrodinger equation for the free particle, though they are not themselves normalizable and therefore cannot represent physically realizable states, could be used to construct physically realizable states. What that means is that we can take those solutions which themselves are not real and can add them up in a way that we can make something that is real. This is a little subtle. We're constructing something called a wave packet, and basically what that amounts to is adding up a bunch of infinities and getting something finite. Taking these traveling wave solutions to the time-independent Schrodinger equation for the free particle, which extend from minus infinity to infinity in the spatial domain, and from minus infinity to infinity in the temporal domain, and summing them up somehow to get something that is localized in the spatial domain. What that means is that we're making a wave packet. A wave packet, the features that we care about is that it's going to be 0 for, say, large negative values of x, 0 for large positive values of x, and only non-zero over some domain. What it might look like is, well, 0, some wave activity over a relatively limited region, and then going back to 0. We will see wave packets that look like this later on. I'll give a more concrete example and show some animations. But for now, let's think about the math. How would we go about constructing something like this? What we did in the case of the particle in a box, the infinite square well potential, was when we solved the Schrodinger equation, we got solutions. If our potential looks like this, going to infinity at regions outside of a box, our solutions looked like this. We got sinusoids with an integer number of half wavelengths fitting in our box. That was nice because it allowed us to construct our overall solution to the Schrodinger equation, psi of x and t, as an infinite sum of these stationary state wave functions. The integer number of half wavelengths fitting in the box, plus the essentially trivial time dependence that you get from the time equation when you do separation of variables with the general Schrodinger equation. This isn't going to work for the case of the free particle for a couple of reasons. First of all, instead of having a discrete sum over, states which have an index n, for instance, this is our psi sub n, where n goes from 1 to infinity, we now have wave functions psi that are continuous. We did not have quantized states. So our stationary states now are going to have to look like our traveling waves. They're going to have to look like e to the I, k, and then x minus, where did it go, h bar k over 2m t. This was our traveling wave solution from the last lecture. So instead of having our discrete set of states indexed by n, we have our continuous set where the parameter is k. K is a completely free parameter, not fixed to be an integer. The second reason our machinery for the particle in a box won't quite work is this coefficient c sub n. C sub n is also going to have to somehow become a function of k. K now being unrestricted, we can't just treat it as a set of discrete entities. We have to have some function, and that function is conventionally written as phi of k. And finally, this sum out front. Again, we can't do a sum if we have a continuous set of functions that we're working with that we want to add up. We have to do an integral. The integral now is going to be an integral over k. So our sum over n became an integral over k. Our coefficient subscript n became a function of k. And our discrete set of functions, psi sub n, became these traveling wave solutions with the parameter k in them. Our integral dk goes over all the possible values of k from minus infinity to infinity. And this is what the expression is overall going to look like. We have an integral, we have this continuous function, and we have our traveling wave states. The main problem with this expression is this guy. How do we know? How do we find phi of k? Phi of k is a general function. What we had done to find the analog of this was that c sub n in the case of the particle in a box. What we did for the case of the particle in a box was use Fourier's trick to collapse the sum. Instead of a sum now we have an integral, and it's not immediately clear from looking at this what it means for an integral to collapse. We'll see what that means in a second. But first of all, let's go back to what we did in the case of the particle in a box and spell out some of the details so that we can make an analogy. On the left-hand side here now we have the results for the particle in a box, whereas on the right-hand side we have the results as I have outlined what they might look like for the free particle. So the first thing we did for our particle in a box was to express the initial conditions as an infinite sum of the time t equals 0 form of our stationary state wave functions. The second thing we did in manipulating this expression to attempt to find a formula for the c sub n was to multiply on the left by a particular stationary state wave function, not n, m. So we multiplied by root 2 over a sine m pi over a x psi of x 0. This is now looking at the left-hand side. So we multiplied by this, and we integrated from 0 to a. This integral is taken dx. It's important to note now that this is not the wave function psi, this is the complex conjugate of the wave function psi, and we'll come back to that in a moment. This integral, this is our left-hand side. If we do the same thing to the right-hand side, you end up with an integral dx that you can push inside the sum. You can pull out some constants, and all you're left with then, the only x dependence comes from the sine function here and the sine function you're multiplying in. So we ended up with the sum from n equals 1 to infinity of c sub n, our two root 2 over a factors from our two wave functions multiply together, just give us 2 over a. And what we're left with inside the integral is sine of m pi over a x sine of n pi over a x dx. So that was our expression, and the nice feature about this is that the sine functions had an orthogonality condition on them that allowed us to take this integral from 0 to a and express it as delta mn. The sine functions, if m is not equal to n, will integrate to 0 over this interval. And if m is equal to n, you just end up with 1. I should be including this factor out front in the expression for the orthogonality. What that means is that the sum collapses. The only remaining term is the term from Cm. So our right-hand side just becomes Cm. This gave us our formula for Cm being equal to the integral from 0 to a of essentially root 2 over a sine m pi over a x times our initial conditions, psi of x 0. This was a very brief overview of what we did back when we were talking about the particle in a box. Now, continuing this analogy into our free particle case, again, the first thing we're going to do is left multiply by the complex conjugate of the wave function. Now, the wave functions that we're working with now are stationary state solutions to the time-independent Schrodinger equation for the free particle. And what those look like, if I evaluate them at t equals 0, is e to the minus I k x. Now, I'm leaving off normalization constants because I don't know what they are at this point, but while I have a k in this integral, I shouldn't use k here. This is the same as saying I have an n in this sum, so I shouldn't use n in the function that I'm multiplying through. Things will just get confusing. So I'm going to call this k prime. So I've left multiplied by k prime. I have my wave function, my initial conditions, and again I'm integrating. Now I'm integrating from minus infinity to infinity, and I'm integrating dx. This is what I get for the left-hand side, just following by analogy from what we did for particle in a box. The right-hand side, in this case, Now, instead of having a sum over n, I have an integral over k. What I'm multiplying by from the left is again the e to the minus I k prime x, but this integral that I'm doing, that's an integral dx. So I can exchange the order of integration by k and integration by x. So I'm going to write this right-hand side now a little differently. We have the integral of minus infinity to infinity dk. Then we have phi of k, which is not a function of x, so I can pull it out of my integral over x, same as I could pull my c sub n out of this integral dx. Sorry, phi of k, not phi of x. What I'm left with then is the integral from minus infinity to infinity dx, e to the minus I k prime x, e to the I k x. Now, in order for this term to be meaningfully, in order for this integral to collapse, like the sum collapsed here, we have to have some sort of orthogonality condition. The orthogonality condition for the sine functions from 0 to a was fairly straightforward. The orthogonality condition that applies here for this, where we are integrating over an infinite domain of something with a continuous parameter, k prime and k are continuous parameters that can take on any value, is not a simple Kronecker delta. It's a little different, but it looks very much the same. What you end up with here is called a Dirac delta function, and we will meet these Dirac delta functions in more detail later. If you're interested, there is a video lecture posted on the Dirac delta function and what its properties are. But for our purposes here, this expression evaluates to a Dirac delta function. A Dirac delta function is defined essentially as an infinitely narrow distribution. If you treat this as a distribution that only is non-zero at a particular value, the delta function by default is defined to be non-zero only for its argument equal to 0. This is effectively a distribution that only has non-zero values, only has support for k equal to k prime. If you treat this as a distribution, and you examine the expression integral from minus infinity to infinity dk of phi of k delta of k minus k prime, if this is a distribution, we're integrating a distribution times a function. This is the expected value of phi of k, subject to the distribution given by the delta function. The delta function, acting like an infinitely narrow distribution, then simply pulls out the value that phi of k has when k equals k prime. Since this is infinitely narrow, phi of k is effectively a constant over the non-zero domain of the delta function. So it's just effectively averaging a constant over this domain. So this whole integral here is equal to phi of k prime. That's what it means for an integral to collapse. And like I said, if you're not entirely clear on how the delta function works, there's another video lecture on how to go about, or how to understand what the delta function can do for you. For now, notice that we can re-express this phi of k prime then in terms of our left-hand side. Phi of k prime is equal to the integral from minus infinity to infinity of e to the minus I k prime x psi of x 0 integral dx. This completely determines phi of k. This is the real genius behind what's called Fourier analysis. What we were talking about in the case of the particle in a box was really Fourier series, and now we're talking about Fourier analysis. The way the math behind this is usually defined is in terms of something called the Fourier transform. The top two equations here are essentially definitions of the Fourier transform. We have some function of x. This is like our wave function as a function of time, and it's being expressed as an integral of some function of k. multiplied by e to the ikx, integral dk. This function f, capital F of k, can be determined by essentially what we did in the previous slide. An integral from minus infinity to infinity dx of the function lowercase f of x times e to the minus ikx. The 1 over root 2 pi factors here are customary. Some authors use them, some authors define them slightly differently. It depends on the specific definition of the Fourier transform that you're using. But you can see the nice symmetry between these two equations. You have your 1 over root 2 pi in both equations. You have an integral from minus infinity to infinity in both equations. You have e to the ikx here, positive, and e to the minus ikx here, negative. That's the only difference. Then you have a function of k, integral dk, function of x, integral dx. Up to labeling x and k differently, the only difference between these two equations is the sign in the exponent. There's a lot of really nice math that comes from using Fourier transforms. Just to give a very brief example, if you're interested in processing astronomical images, for example, or any images really, treating the image as a function of this k parameter, which is a spatial frequency parameter, instead of treating the image as a function of x, as a function of which pixel you're looking at, you can do some very powerful analysis to identify features, for instance. High spatial frequency features versus low spatial frequency features. Smoothly varying backgrounds versus the boundaries between objects where the image varies rapidly will have different behavior when expressed in terms of this function of the spatial frequency. From the perspective of quantum mechanics, what we're interested in is how to express our wave function as a function of position and time. Well, using the Fourier transform definition here, we can find this phi of k by the same sort of equation. Phi of k is determined by an integral dx of our initial conditions times a complex exponential. Knowing what phi of k is, we can then determine what phi of x and t is. So again, our initial conditions determine our constant multiples essentially of our stationary states, these complex exponentials, which then gives us our overall wave function and how it behaves. To check your understanding, here is a simple example problem that requires you to apply the formulas on the previous page to go from a particular initial condition. In this case, it's a constant. Our initial wave function looks something like this. 0 everywhere except for a region between minus a and a. Your task, find the phi of k that goes with this particular function. That's about it, but before we finish talking about how to superpose these solutions, I want to look at the solutions themselves in a little more detail. Let's talk about the wave velocity in particular. This is our traveling wave solution, and we can figure out what its velocity is by looking at this argument. Which direction is this wave going? Well, if we look at a particular point on this spiral, on this e to the ikx, as time evolves, we can figure out where that point on the spiral is by setting this argument equals to a constant. Since I don't really care about what that constant is, I'm just going to set that equal to 0. So let's say kx minus h bar k squared over 2m t is equal to 0. If I continue along these lines, it's clear that in this case, if t increases, this part of this expression is getting more negative. This part of the expression has to get more positive. So that means x has to increase as well. So as t increases, x increases. That means this wave is moving to the right. The next question I can ask is how fast? How fast is it moving? And if you look at this again as setting this expression equal to 0, I can solve this and say x is equal to h bar k over 2m t. And in this case, the velocity is pretty clear. we have this constant, x equals some constant times time. Position equals something times time. This is our velocity. What this actually is, in terms of the energy of the particle, requires knowing what the definition of k is. So we have h bar over 2m, and the definition of our k was root 2me over h bar. So our h bars cancel out, and if we finish this expression, moving the 2m effectively under the square root, we get the square root of e over 2m t. So the velocity we get here is square root of e over 2m. Now, classically, what we get, we have a particle moving at some velocity and it has some energy. We know the relationship between those. It's the kinetic energy. 1/2 mv squared gives me E. And if I solve this, I get v squared equals 2e over m, or v equals root 2e over m. These expressions are not equal to each other. That's a little strange. The velocity that we got from quantum mechanics, looking at how fast features on this wave function move, is not equal to the classical velocity. Will this hold true regardless? Do quantum mechanical particles have a different propagation behavior? That doesn't really make a lot of sense. This is actually not a problem, because what we're measuring here is the velocity of a feature on this wave. It's not actually the velocity of a wave packet. And since wave packets are the only real states that we can get, that we expect to observe in the physical universe, what we need to figure out is the wave packet velocity. In order to figure out the wave packet velocity, consider this wave packet. This is just a sum of two traveling waves with different k's, which I've now indexed k1 and k2. What I'd like you to do is think about expressing k1 and k2 as if they were near each other. So k1 is slightly less than k2, for example, or k1 is slightly greater than k2. Under these circumstances, it makes sense to rewrite these things. I'm going to define alpha as k1 plus k2 over 2, the average, times x, minus h bar k1 squared plus k2 squared over 2m t. Essentially, the sum of the argument of this and the argument of this. I'm also going to define a parameter delta, which is k1 minus k2 over 2x minus h bar k1 squared minus k2 squared over 2m t. Actually, sorry, I don't mean 2m's here. I mean 4m's here. Because I have a factor of 2 from the over 2m, and I have a 1/2 essentially from the way I'm combining the two terms. So given these definitions, you can express this as, not writing it there, as e to the I alpha plus delta plus e to the I alpha minus delta. So you see what I've done here? I've just re-expressed the arguments here as sums and differences. This is getting into the idea behind sum and difference and product identities in trig functions, except I'm doing this with complex exponentials instead. If I write this function as alpha plus delta, when I add alpha and delta, for instance, this first term gets me k1 plus k2 plus k1 minus k2. The k2's drop out, and I end up with 2k1 over 2, which is just k1 times x. Just k1x, essentially, what you want to get from this. If I express these exponentials in that way, you can factor out the alpha part. You get an e to the I alpha times an e to the I delta plus e to the minus I delta. If you're familiar with the complex exponential form of trig functions, you can probably see where I'm going with this. This is going to end up equal to e to the